All right, you guys. So right now for number one, we have that point P has coordinates negative 3, comma 2, and point Q has coordinates 15, comma negative 8. They tell us that point M is the important word midpoint of PQ. And so for part A, we need to find the coordinates of M. Now guys, for this whole paper solution, the method that I like to show is that once you identify buzzwords, which is like keywords, if you want to think about it this way, like very important words, this allows you to find the correct procedure and oftentimes the correct formula to use. All right. So let's always focus on the buzzwords, always focus on the keywords, and this is a big hint for which procedure or formula to use. So in this case, the big buzzword here is midpoint. So what is a midpoint? The midpoint, quite literally, is the middle between 2 points. So for example, here you have A and here you have B, okay? The midpoint is going to be right around here. It's right in the middle. So if this whole distance is, I don't know, 6, that means here you have, from here to here you have 3, from here to here you have another 3, okay? So that is what a midpoint is. And for finding the coordinates of M, of the midpoint, there is a formula. And so the day of the test, you guys, you will be walking in with the formula booklet. And so why do I talk so much about knowing the buzzwords well and the keywords well? Because once you know the keywords well and the buzzwords well, a lot of times they're in your formula booklet. Guys, the day of the test, you're walking in with like, 2 years of experience in this thing called IB, 2 hours of sleep, a lot of motivation to do well, a calculator. Well, for paper one, you don't have a calculator. Um, a formal booklet, a pen and pencil. See? And so the formal booklet is a tool that you can use the day of the test. So get familiar with it. So once you identify midpoint, you look for midpoint over here, and eventually you're gonna find this. So on the one hand, you have midpoint for x, y, and z, okay, which is a graph that looks like this. So here you have x, y, and z, all right? And for the other formula of the midpoint is quite simply for just x and y, okay? So this is the more classic, the more friendly, and this is the formula we're going to be using. So the midpoint formula for part A is your midpoint equals x1 plus x2 divided by 2, comma, y1 plus y2 divided by 2. And just so that we're all on the same page, this right here is really just a set of points. Okay, it's an x comma y. Your midpoint is a set of points. All right, so this is just an x comma y. And what does the little one do? What does the little 2 do? This is just your first point and your second point. So for example, your first point is x1 with y1. Your second point is x2 with y2. Ah, that makes a little bit more sense. So x1 is negative 3, y1 is 2, x2 is 15, and y2 is negative 8. And now that we understand all of that context, suddenly this becomes way more friendly. And I go ahead and plug into the midpoint formula. So for this first one, I end up with x1 we said was negative 3 plus x2 is 15 divided by 2, comma, y1 we said was 2 plus y2 we said was negative 8. So plus minus 8 divided by 2. So the plus minus 8 just ends up as negative 8. And my midpoint ends up being, on the one hand, I have 12 divided by 2. Another one, I have negative 6 divided by 2. So that means that my midpoint officially is now going to be 6 comma negative 3. So that is for part A. Later on, they tell us that line L is perpendicular to PQ and passes through M. So which is the keyword here, you guys? The keyword here is perpendicular. Now, for perpendicular, I don't think it's in a formal booklet. No, it's not. So this is something you have to sort of learn by heart, okay? Perpendicular makes reference to slopes, okay? And so the two types of slopes that you can encounter for part B, okay? The two slopes that you can encounter, because for part B they ask, find the gradient of L, see? So L, we know is perpendicular and passes through M, see? So L is a line, And so for getting the equation of a line, your main tool, and this is here in your formal booklet, so equation of a line, equations of a straight line, I think it was, yeah. So here are your three equations of a straight line, see? You use these for different purposes or whatever, okay? But my suggestion and what I want you to really put into your brain is that for creating lines or for creating equations of a straight line, the one you're going to pretty much always use is this one. This one is called point slope formula. Now let's take a moment, let's look at it, let's understand what it's asking for. And so in order to create the equation of a straight line, all you need are this, this, and this. Okay, if you plug in those three things, you're good to go. So y1 and x1 is a set of points. So if you have a point, you're halfway there. And if you have m, you're good to go. Now what is m? M is the gradient. What is gradient? Gradient is slope. Okay, so the moment you have a point and the moment you have a gradient, you can use this equation here and you create the equation of your line. Now, back to reality. In part B, they tell us that line L is perpendicular, so this is a big hint for M, okay? Like your slope, so slope M. I know there's two M's here, so I'm going to put slope M. And they tell you that it passes through midpoint M. And so midpoint M, we said, was 6, negative 3. So for the point slope formula, which uses y minus y1 equals m times x minus x1, I already have my y1 and my x1 because we're going to be using the midpoint from part A. But for the slope, I still need to figure it out. And so the keyword of slope is perpendicular, okay? So I'm going to talk a little bit about that right now. So your slopes, there are two types, okay? You have, like special types, right? So you have parallel slopes and you have perpendicular slopes. The hardcore math definition that I'm going to give you is that when your slopes are parallel, the slope of the first equals the slope of the second. That is why I'm putting 1 and 2, okay? While for perpendicular, the slope of the first times the slope of the second equals negative 1. Now, how does it look visually? Parallel lines look something like this, okay? So they travel on forever and they never touch each other because they have the same slope, because they are always growing at the same rate, and so they will never touch each other. If they were growing slightly at a different rate, eventually they would touch each other, okay? But in this case, parallel lines have the exact same slope. For part B, they tell us we have perpendicular slopes. And so perpendicular slopes, how does it look like? It looks a little bit like this. Okay, it's two lines that cross, but they cross in a way, they intersect in a way that you have 90 degrees all around it, okay? And so they are perfectly sort of like, kind of like mirrored, okay? Just intuitively have that idea. They're kind of mirrored, they're kind of like perfectly opposite and stuff like that. And so, it's not exactly that, but intuitively I want you to have that idea. Perpendicular lines look like this, okay? And 90 degrees show up all around it, see? And so the hardcore definition is that the slope of the first times the slope of the second equals negative 1. Now, what a lot of you guys have probably been taught is that for perpendicular slopes, m1 is going to equal, if I get m1 alone, right? So you divide by m2 to both sides, right? So that means that m1 is equal to negative 1 times 1 over m2. And so this is what you might have heard as the negative reciprocal. So negative because you have a negative 1, and reciprocal because you're flipping the slope. So if your slope is, I don't know, 7, for example, if the slope of your line 1 is 7, and you know it's perpendicular, the slope of line 2 is negative 1 over 7. If line 1 is negative 4, then the negative reciprocal is that you flip it, and you put a negative, right? So it's negative 1 over 4. It's just 1 over 4. And another example, let's say you have 1/2, so the perpendicular of this would be negative 2, because you flip it and you put a negative. Right, so that was a pretty long explanation, but I'm sure someone out there needed it, so this one's for you, okay? Yeah. So perpendicular slopes is the negative reciprocal, and so the slope that I know, actually you don't know a slope. You first need to find the slope. So this got even more interesting, see? And so the gradient of L, which is what they're asking you to find, is perpendicular to PQ. And so that means if I find the slope of PQ, I just need to do the negative reciprocal, and that gives me the slope of line L. So what is the slope of PQ? Well, the formula for slope is right here. It's y2 minus y1 divided by x2 minus x1. So just to be a lot more organized in this approach, let me erase here a little bit. So first, we're going to find the slope of PQ. So slope PQ is, so slope PQ, the formula first is m equals y2 minus y1 divided by x2 minus x1. Some of you might have been taught that the slope is rise over run. And here it makes sense how the formula looks, because your y values, which are vertical for rising, are on top, so that's why rise is on top. And for running in horizontal, you have your x values. So that's why y is on top and x is on the bottom, rise over run, okay? Anyways, so the slope PQ, well, you have 2 points, right? So you have the point P, which is negative 3, comma 2, and you have the point Q, which is 15, comma negative 8. So if you use the gradient formula here for the slope, you end up with m of this guy, so m PQ, okay? Just to be more organized, so your m of PQ is going to be y2, which is this guy here. So this is y2, this is x2, this is x1, this is y1. Which is going to be y2, which is negative 8, minus y1, which is 2, divided by x2, which is 15, minus x1, which is negative 3. So on the bottom, you have negative, negative. So up top, it's negative 10. On the bottom, you end up with 15 plus 3. So that means the slope is going to be negative 10 over 18. Okay? And if you want to get fancy, you would simplify this a little bit. Because they're both even, you can divide both by 2. You end up with 5 over 9. Okay? So basically, the slope of PQ, okay, is 5 over 9. And this is enough for you to say that the slope of L has to be the negative reciprocal. So it's going to be negative 9 over 5. All right? And I just noticed, my bad, you guys, but I'm going to leave it in the video because we all make mistakes. There was a negative right here. And I forgot to put it here. See? So we all make mistakes. We all need to double check sometimes. This negative should have stayed here. So that means that over here I put negative 5 for slope of PQ. So that means that the negative reciprocal ends up being negative 9 over 5. So it's just positive 9 over 5. So my gradient, finally for part B, my gradient is 9 over 5. And last but not least, you need C. Hence, write down the equation of L. Now, I told you guys way earlier, I did get a little bit ahead of myself, but for writing down the equation, you need the best, in my opinion, is the point slope form. See? And so the point slope form, what it needs is a set of points and a slope. And so the set of points, I already have it, because as I mentioned earlier, the set of points we're going to be using is the midpoint. And the slope you're going to be using is the one we just found, right? And so for part C, you just need to plug all of that in. So it ends up being y minus negative 3, because of this guy here, right? Equals your slope, because of m, so 9 over 5, times x minus your your x1, right? Minus 6. So y plus 3 equals 9 over 5x minus 9 times 6 divided by 5. So y plus 3 equals 9 over 5x minus quick maths gives me 4554 over 5. All right, and technically, from here, you're like good enough, okay? From here, you're fine. But just to show like the whole process and just to get full credit or whatever, technically from here, it's already good enough, okay? I'm just looking at the answer key. I'm just gonna be transparent with you guys. You can leave your answer as this, okay? Which is like pretty much the first step of using the point slope form. So apparently that's good enough, but I'm a guy that would rather play it safe and like go all the way. So if we go ahead and go all the way, you want to get this guy alone. See, you want to get y alone. You want to reach y equals mx plus b. And so to reach y equals mx plus b, you need to get y alone, so you can do minus 3 to both sides. So that means you end up with y equals 9 over 5x minus 54 over 5 minus 3. So that means you have y equals 9 over 5x minus 54 over 5 minus, and here you need to amplify, right? So you amplify by 5. So you end up with a 3 that is times 5 on the top and on the bottom. This allows you to combine the fractions. So 9 over 5x minus 54 minus 15 divided by 5. Okay, so y equals 9 over 5x minus 69 over 5. Okay? And so as long as you show all your process, they definitely give you the point up here. I'm the kind of guy that like gets stressed out and would rather just go all the way, so might as well show you how to reach the form y equals mx plus b for any future exercise, okay? Anyways, that was a little bit of a long explanation, but I'm sure someone needed it, so here it is. I hope it helped, and I'll see you around. All right, you guys, so now for this second one, okay, we have that the function f is defined by f of x equals this whole thing, which looks a little bit nasty, I'll be honest. For x, x this, and x that. So let's explain this just for a second to understand what this is telling me. So when it says this symbol here, okay, it means that your values of x are within all real numbers, okay? And if it's within all real numbers, it's basically like there's nothing weird going on. See, it includes all real numbers. There's nothing like special happening here. It's just telling you that x pertains to all real numbers. See? So from negative infinity to positive infinity, you include all numbers in between. This might be important in another exercise if they tell you that x pertains only to, for example, z, which is like a very fancy z. This would be integers, okay? And integers are -3, -2, -1, 0, 1, 2, 3, okay? So it would be whole numbers, right? And so a detail like that can be very relevant, but if they tell you it belongs to all real numbers, it's nothing you need to like be careful for, okay? But that is what this symbol says. See, it's like x pertains to like this set of numbers or whatever, okay? So that is more of an intuitive way to put it, and I'd rather explain things intuitively. The x cannot equal 2 has to do with what your fraction has, okay? And so sometimes, because of how your function is set up, there are certain values that x cannot take. There's one or two classic examples, okay? On the one hand, 0 divided by 3, you guys, is how much? Is 0. 3 divided by 0 is how much? It's undefined. You cannot divide by 0. It is illegal. Don't do illegal things. Usually, I suggest that you should not do illegal things, okay? So if you divide by 0, it's illegal, it's undefined. So why can x not equal 2? It cannot equal 2 because in the denominator, basically this whole thing cannot equal 0, right? And so 2x minus 4 cannot equal 0. And if you get x alone from here, 2x cannot equal 4, divided by 2 to both sides, x cannot equal 2. Ah, so that is where it comes from. See? That is where it comes from. X literally cannot equal, sorry, the denominator cannot equal 0, so that means x cannot equal 2. So that is one example that can sort of show up that restricts the values of x that you can take. That is one classic example. The other classic example is, for example, like a square root. See? So imagine you have x minus 3 here. The point is you cannot have a negative inside of a square root. Okay? It's unsolvable without using imaginary numbers. Okay? Which is a whole other thing that I'm not going to get into, but usually the idea is whatever's inside has to be greater than 0. And so in this case, x minus 3 has to be greater than 0. X has to be greater than 3. Okay? So that is just a made-up scenario, but point is, sometimes your domain gets restricted. Your domain is values that x can take, okay? So this thing here is just helping you define your domain. It's all real values except for 2, all right? And this made-up example of the square roots is something that I know can show up for you, so I'd rather tell you. Inside the square root, things have to stay positive. So greater than or equal to 0, now that I think about it. Greater than or equal to 0. Enough blah blah. For part A, we need to find the 0 of f of x. And so for finding the 0 of f of x, basically, when they ask for zeros, they are asking for the x-intercepts. And whenever you need to find x-intercepts, notice, here you have a y, here you have an x. All of these that I'm putting in red are x-intercepts, see? Now, what do they all have in common, you guys? Some of you are probably thinking, well, they're all x-intercepts, right? But what do all of these points, what do all of these x, y's have in common? Ah, all of these, without a doubt, because they are x-intercepts, have a y equals 0. So whenever you're finding an x-intercept, okay, you just need to plug in x, 0. And on that note, if you ever need to find a y-intercept, it's the same thing, but the other way around. If you ever need to find that y-intercept, notice how all of these points, what do they have in common? They have in common that their x equals 0. And so for the y-intercept, you will be plugging in 0, y. So your y-intercept is basically 0, something, while your x-intercept is something, 0. All right? So that is a little bit of an intuition of why we approach this the way we do. Whenever they ask for zeros, it is specifically about x-intercepts. And so that is something we need to associate in our brains right away. Zeros is for x-intercepts, okay? And so we plug in x, 0. So here we have, well, our original, right, is f of x equals 7x plus 7 divided by 2x minus 4. So if you plug in x, 0, that means your y is 0. Now, where is y? This whole thing is y. So this whole thing is now 0, so you end up with 0 equals 7x plus 7 divided by 2x minus 4. And the cool thing you can do here is that because it's a fraction, you can multiply by 2x minus 4 to both sides. And this is very useful because, this goes away with this, and anything times 0 is still 0. So you end up with 0 equals 7x plus 7. I want to get x alone, so I do minus 7 to both sides. So basically end up with 7x equals negative 7. Divide by 7, divide by 7. X has to be, for part A, x has to be equal to negative 1. So for part A, I'm just going to put it up here just to be more conservative with space. So for part A, x equals negative 1. Okay, so that is the 0 of f of x. If you get fancy, you can say that it's negative 1, 0. Okay, same idea. Nothing is changing there. So that is for part A. Remember that zeros makes reference to x-intercepts. A very specific thing you have to remember. For part B, part I, or for part B initially, they tell us that for the graph of y equals f of x, which is basically just this, right? So for your function, write down the equation of, first of all, the vertical asymptote. Now, there's a lot of buzzwords here. So on the one hand, you have vertical, on the other hand, you have horizontal, and then you have this special one, asymptote, asymptote. Now, what the heck is an asymptote? An asymptote is basically an equation or a line. Let's think about it as a line. So it's a line that your function will never touch. Okay, that is actually such a good definition. So an asymptote is a line that your equation will never touch. Is a line that your function, better said, will never touch. And so there are different types of asymptotes, but for us, there will always be vertical or horizontal. So if I go ahead and graph this here, okay, for example, onto decimals, and I know that for this part you don't have calculators, so some of you might be thinking, oh, dude, why are you doing this? We don't have calculators, like, this is cheating. Okay, I'm only doing this so you guys understand what an asymptote even is, okay? And so if you graph your function, right, it looks like that, okay? So you're gonna have two asymptotes, and I'm gonna show you how to find each. On the one hand, you have a vertical one on x equals 2. So notice how my red line never touches the blue one, not even close, okay? Even over here, yes, it gets very close, but it never actually touches it, okay? So here's my vertical one, and my horizontal one is a y value. And I'm going to show you in a second how to actually get that, okay? And so your vertical one, your vertical one is an x value of 2, the one in blue, and your horizontal one is a y value of 7 over 2, see? Now, I know some of you might be a little bit confused by this, see? For example, why is my vertical asymptote, the one in blue, an x value? Like, we have associated x values to horizontal stuff, so why is my vertical asymptote an x value of equals 2? It's an x value of equals 2 because all along the line, what does x equal? Ah, x equals 2 all along my line. And so for the vertical asymptote, you put in a fixed x value, which means that all along the line it's just 2. And for the horizontal one, it's the same idea. It's a fixed y value. It's always 7 over 2. Well, here it puts it as 3.5. See? So that is why, I know it's a little bit counterintuitive, but okay, so for the horizontal asymptote, it's a fixed, for the horizontal one, it's a fixed y value. So you need to put y equals something. For the vertical one, it's a fixed x value, right? And so that is the idea of an asymptote. See? Now, how do you actually find them? Well, for the vertical one, it's a little bit easier because now we have associated in our brains that vertical, okay, is a fixed x value. And so once you find out the values of x that you cannot take, that is the equation of a vertical asymptote. And so here they actually tell you that x cannot equal 2, and the proof is the one I showed earlier, right? So you took the denominator, you said this can't equal 0, right? And so quickly you find out that x cannot equal 2, see? And so because x cannot equal 2, the equation of your vertical asymptote is x equals 2. So the moment you put x equals 2, the blue line shows up, okay? And so careful, it's very important that the equation of your vertical asymptote is x equals 2. You cannot put x does not equal 2 because this is not an equation. You need to leave it as an equation. So x equals 2 allows you to draw the blue line, okay? So that is for part B, part I. For part B, double I, you need to find the horizontal asymptote. And so for the horizontal asymptote, you would be saying it's a horizontal fixed y value. Now, for this one, it's a little bit harder to like figure it out. See? For the vertical asymptote, it's usually friendly because it has to do with, I don't know, you can't divide by 0 or something about like whatever, like it's a square root, so it has to be greater than or equal to 0. It's usually like a nicer approach. See? For the horizontal asymptote, we have to find the equation of this green line. And so the best way I can show you, and I know it's a cheap answer, but it's what works. Okay, the best way I can show you is that you just plug in a very big y value. Okay, because if you plug in a very big y value, like all the way out here, see, I don't know, let's do it like 100. See, so you plug in like 100, okay, you're gonna end up very close to your line, extremely close. See, and so all you need to do is that it's gonna be pretty apparent what number you're close to, what number you almost reach, and that is gonna be your horizontal asymptote. See, and so for this, I know it's a little bit cheap, but basically for horizontal asymptote, plug in really big values. Okay, and so if you plug in really big values, for example, so my f of x, as we said, is 7x plus 7 divided by 2x minus 4. So if I go ahead and plug in something like, I don't know, 100, right? You end up with 7 times 100 plus 7 divided by 2 times 100 minus 4. So that means that I pretty much, okay, end up with 700 plus 7 divided by 200 minus 4. See? So this is pretty much just going to be 707 divided by 200, sorry, 196. See? Now you might be thinking, dude, dividing this is insane. It's very hard. What do I do? Right? I just came up with a smarter way to do this. See? So technically, if you have your calculator, this is a nice approach, and you're pretty much going to end up with 3.5. But doing it by hand is much harder. See? And so let me go back a couple steps, and let's keep the idea of plugging in a really big value. See? So a smarter way to do this, and again, I'm leaving it in the video because oftentimes when we do our exercises, we figure out a smarter way to do it. It's part of the process. So I'm going to leave it, okay? Because I know you go through the same stuff. So if you go ahead and let's imagine for a second that you're like plugging in, I don't know, like infinity, okay? And I know this is kind of whack, but trust me, just trust me for a second, see? So if you go ahead and plug in infinity, think about it for a second. So we have 7 times infinity divided by plus 7 divided by 2 times infinity minus 4. And so when you have infinity going around, which is just a massive number, right? It's just a crazy massive number. And this is not actually how infinity works, but for us intuitively, for the vertical asymptote, I mean for the horizontal asymptote, it's going to help. See? So just think about it as 7 times a massive number plus 7 divided by 2 times a massive number minus 4. How much effect do you think these numbers are going to have? Nothing. They're going to have no effect because they're next to a massive number. So really, you can just think about it this as this, right? Once you plug in infinity, the 7 and the negative 4 don't really matter. And so technically, what you're really looking at is at 7 over 2. And so the equation for the horizontal asymptote is just going to be 7 over 2. Okay? Technically, it also works doing the thing I did by times 100, right? Or you can do it like times a million and then divide and actually figure it out, and you will end up with 3.5, okay? Or you're going to end up with 3.4999999. But for me, maybe more intuitively, it makes sense to do this approach. See, I know it's kind of whack to plug in infinity, but I just used it as an idea to like you're plugging in a very big number, and so once you plug in a very big number, this and this is irrelevant, and that's the whole point because you're going way out in your function, way out to the right, and the 7 over 4 just doesn't matter at that point. So it doesn't matter at that point, and that gives you a green line very close to the red one, and that is the equation you want. See? So again, that was a little bit of a cheap way to do it, but for horizontal asymptote, it tends to be like that. It tends to be plugging in a very big number, and usually with a little bit of imagination, you can get there much quicker. See? So there it is for part B. Last but not least, for part C, we need to find that, which they tell us is the inverse function of f of x. Now, for finding the inverse, thankfully, it is a very sort of straightforward approach, okay? And so, before anything, the inverse is like the mirror of your function, okay? And so for the inverse, the steps are going to be always the same, see? And this is just the steps I suggest. I know there are others, but these are the steps that I suggest. So the steps that I suggest is that first you write down the OG. So put the OG function, the original function, okay? So put the OG. Then put f of x as y. And so now I haven't done anything yet besides just putting f of x as y. And now the third step is going to be flip x and y. And this is the key step. The moment you flip x and y, you're now finding the inverse. See? So if you flip x and y, that means you end up with x on the left equals 7 times y. Ooh la la, plus 7 divided by 2 times y minus 4. And now that you flipped x and y, get y alone. Okay? So if you get y alone from here, well, again, because it's a fraction, I highly suggest that you multiply both sides like this. And so this first step of multiplying is usually going to be like that. So on the left side, you end up with 2yx minus 4x equals 7y plus 7. Now, because our mission is to get y alone, put all the y's on one side. So I'm going to do minus 7y minus 7y. That means I end up with 2yx minus 7y minus 4x equals 7. And so now you want to get y alone, so you do plus 4x plus 4x. So 2yx minus 7y equals 4x plus 7. And so from here, now that you have all the y's on one side, see? So notice how here you had a fraction, so you needed to multiply, right? Over here, you had the y's on both sides. And now, once you have all the y's only on one side, you can factor. And so if you factor on the left side by y, that means inside, like if you take y out from each, you end up with 2x minus 7. Ah, interesting. And so now to get y alone, right, you can just divide. So here, because it's multiplying, you can divide by 2x minus 7 to both sides. So that means that this goes away with this. You end up with y equals 4x plus 7 divided by 2x minus 7, right? And so now that you got y alone, your last step, just to be very organized, is put the inverse, or put y, sorry, put this new y as the inverse, see? And so this is just to be very rigorous in your approach. So you're just going to change the symbol here. So your inverse function is going to be this, see? And that is for part C, right? Now, the last step you have to do is that, okay, you need to put the detail, okay? You need to put the detail that the denominator cannot equal 0, right? So what value can x not take? Well, the value that x cannot take is that your new denominator cannot equal 0. So this cannot equal 0. So plus 7 to both sides. 2x cannot equal 7. So that means that x cannot equal 7 over 2. And so your final answer is putting the detail that x cannot equal 7 over 2. And that is for finding the inverse. See? So again, a little bit of an annoying process, but it's always the same. The big step you have to do is step number 3. Okay? Anyways, you guys, that is for number 2, and I hope it helped. Alright, and now for number 3, we have that on a Monday, happy Monday, At an amusement park, a sample of 40 visitors was randomly selected as they were leaving the park. And all these homies, they were asked how many times a day they had been on a ride called, whoa, the Dragon. The information is summarized in the following frequency table. So let's first understand this frequency table and what it means. So, for example, one of the persons they interviewed for the number of times they were in the Dragon, he answered 0, right? Now, how many people answered 0? 6 people answered 0. Of the 40 visitors that were surveyed, of those 40, the ones that rode only once were 16. The ones that rode exactly twice were 13. The ones that rode exactly 3 times were 2. And the ones that rode exactly 4 times were 3. Okay, that is a better explanation than to what I was about to do. So that's the frequency table. Okay? It can be assumed that this sample is representative of all visitors to the park for the following day. Alright, so for the following day, we can basically estimate using the same table. So we can trust the table as a good representation. So for part AI, we need to find the probability that a randomly selected visitor will ride the dragon. See? So guys, for probability, the name of the game is always the same. So for probability, it's your total cases in the bottom. So total cases. And up top, it's possible cases for what you're trying to find the probability of. And so the probability of ride is going to have all the possible cases. So all that ride divided by the total cases, which is all that went to the park. See? So intuitively, I can state it like this. Basically, you just need to sum all the possible cases divided by the total cases. So all the possible cases, right, of those that rode is going to be these, and these. And your total is going to be these. Okay? So notice, for the total, it's that in red. And for the possible cases, it's just the ones in orange, in red, in blah, fuck, in green. Okay? So technically, I can do 16 plus 13 plus 2 plus 3 divided by 6, which includes this guy, plus 16 plus 13 plus 2 plus 3. So you can spend some time doing math, but eventually you're just going to find that you have 34 divided by 40. And so that is one way to do it. The other way to do it, which is a more like quick maths sort of approach, if you want to cook this for a little bit, you can see that they tell you that it's 40 visitors. So your total has to be 40. All that went to the park were 40. And they're only asking for those that will ride the dragon. So which ones don't ride the dragon? 6 of them don't ride the dragon. So you can do 40 minus 6. It gives you this 34. See? So that is a slightly quicker way to just find 34 over 40. See? I don't know if it's that much faster, but I do want you to see it as an option. Okay? Anyways, for part AI, the answer is 34 over 40. That is a probability that they will ride the dragon. So let me make a little bit of space over here. And let me just write that real quick. The answer for part AI is 34 over 40. For part A double I, we need to find the expected number of times a visitor will ride the dragon. And so here we enter what we call expected values, expected number, expected. And so the big word, the big buzzword here is expected. Now, once you find the expected thing, okay, once you realize that they're asking for expected, it's suddenly very easy to do this. See? So all you need to do for expected is just a very visual approach. See? So you're going to be doing, for example, this times the probability of that. This times the probability of that. This times the probability of that. So on and so forth. Now, how do I know that you need to do this? I know this because it's actually in your formula booklet. So in your formula booklet, if you eventually find expected value, here it says, expected value of a discrete random variable x. Discrete, you guys, is just like a whole number, okay? And so here you have a bunch of whole numbers, 1, 2, 3, 4, right? So that's why you know you can use this. Now, what is this saying? It's basically the sum of your, it's going to be the sum of your x's times the probability of each x. So it's going to be each x, it's going to be the sum of all of these, right? The sum of your x times the probability of getting that x. So now it's a little bit more friendly because, okay, so basically it's just, for example, for this first one, it's 0, because that is my x, right? Times the probability of getting that x. Now the probability of getting that x is, so it's going to be 0. The probability of writing 0 times is 6 over 40, because the frequency is 6, right? And for the next one, because we're adding, right? It's a summation. See, we're adding. So this is for the first one, right? Then for the next one, we have that it's, okay, writing once, what's the probability of that? So writing once, the probability of that is 16 over 40. 16, because this is frequency 16. All right, interesting. So you can keep going from here. Plus 2 times, so what's the probability of writing exactly twice? 13 over 40. And you keep going and you end up with something that looks like this. So for 3, it's going to be 2 over 40. And for 4, it's going to be 3 over 40. Okay, because of this 3. And so that is for the expected values. If you do all the math, you're going to get the right answer. Now, I know some of you might be thinking, you're trolling. Why did you put this 0 over here? And I put it just to follow the procedures, just to show how you're supposed to do it. See? And so for this first one, yes, it ends up being 0. It doesn't really matter. But I would rather just show you the whole process. Okay? So on the one hand, that happens with that. This next value ends up being with 1 times this is just 16 over 40. Then the next one is 2 times 13, so it's going to be 26 over 40. Plus 3 times 2 is 6 over 40. Plus 4 times 3 is 12. Whoops. 12 over 40, right? So you go ahead and add all of these. It's pretty friendly because they're all in denominator with 40, so you can add them as a fraction. So you end up with 16 plus 26 plus 6 plus 12, all under the same 40, right? And this, with a little bit of quick maths, ends up being damn, I cannot math right now. So that is 18. Then that is yeah. It ends up being 60 over 40. Okay? And so 60 over 40, if you were to, simplify this a little bit, on the one hand, they both have a 0 on top, so you can do boom, boom. You end up with 6 over 4. They're both even, so you can leave it as 3 over 2. So I'm going to leave it as 3 over 2. Okay? So for part A, double I, the expected number of times a visitor will ride the dragon is 3 over 2. If you want to get fancy, this is the same as 1.5. Okay? I'll leave it as a fraction because whatever. See, we're working with fractions. Then they tell us that it is known that 1,000 visitors will attend the amusement park on a Tuesday, and the dragon can carry a maximum of 10 people each time it runs. And so we need to estimate the minimum number of times the dragon must run to satisfy the demand. So let's take a moment to think about this. See? Usually for the IB, not always, but usually, and it's a big hint, what you do in part B needs something from part A. It's not always the case, but a lot of times it is. Okay? And so here, part A double I is something directly needed for part B. Okay? So, the expected number a visitor will ride the dragon, we said it was 3 over 2. Okay, we said it was 1.5. And so, technically, if 1,000 people show up, then how many times will they ride the dragon? Well, one person, so one visitor, rides 1.5 times. So 1,000 visitors, you need to multiply this by 1.5 to find the amount of times that the dragon is ridden. And so 1,000 times 1.5, right? Well, quick maths, you end up with 1,500, okay? There's a chance that you kept it as fractions and you didn't realize the decimal, so you can leave it as times 3 over 2. This is just going to be 1,000 over 1, right? Times 3 over 2, because for fractions that multiply, you multiply straight across. So I put a 1 over here just to make it more visually appealing. You end up with 3,000 divided by 2. This gives you the same 1,500. So this 1,500, you guys, let's leave very clear, is number of times the dragon is, I actually don't know the right word here, is ridden, is rode, is used, okay? So that is the number of times the dragon is used. And because the dragon can carry a maximum of 10 people, the minimum number of times it has to run to satisfy the demand is 1,500 divided by 10. So if you divide by 10, because they both have a 0, you can do couple out, 150 times. So that is for part B, and that is for number 3. Alright, you guys, and now for number 4. Number 4 is hard. And so number 4 for part A asks us to show that the equation cosine 2x equals sine x can be written in the form of this, okay? And so from here, part A is relatively easy, and part B just goes crazy, which makes sense because part B is worth 5 points. So if you take the time to learn this, you can get a whole lot of flipping points, okay? Anyways, so we're going to be writing a lot for this, and I'm probably going to need more space than this, so I'm going to be using my whiteboard over here, see? So here in this whiteboard, basically for part A, the main thing we need to notice is that we need to pass from cosine 2x equals sine x to this whole thing here, of course. But what is important about this, the thing that I'm putting right now in yellow only has sine. There is only sines going around, while originally we have a cosine. So if you get rid of cosine, you're good to go. Now, what are your tools for getting rid of cosine? Your tools for getting rid of cosine in your formula booklet, eventually, once you get familiar enough with it, and this is something I invite you to do. I invite you to study with your formula booklet. Get used to it, because the day of the test, you are walking in with the formula booklet. It is an additional tool that you can use. So get friendly with it because it's going to save your life. Anyways, eventually you find this. So these are the main tools you have for facing these type of exercises. Okay, anything that looks anything remotely like what they're asking here, you're going to be using these tools. And so these tools, I copied and pasted over here. Okay? Yeah. So for part A, now that we understand our tools and our approach and everything, we have cosine 2x equals sine x. And my only objective for now, because a lot of times we're like, oh, we need to reach this, and you focus so much on this, and you get like confused or whatever. The main idea is just get rid of cosine. Once you get rid of cosine, everything will flow. And so let's get rid of cosine slowly but surely. So which of these properties, specifically this 3, because we don't have tangent up here, so we're going to forget about that. Of those 3 properties, which ones could help me? All right, so we can start off with the one that is down here. See? So for the one that is down here, it literally has cosine 2 theta. Now theta is just what's inside the cosine. In this case, we have, the x, right? Well, actually, this whole thing is inside the cosine, my bad. But point is, instead of theta, here we have x, but the formula works the same. So cosine 2x can turn into this here, okay? So if I go ahead and do that, okay, if I go ahead and do that, I end up with, on the left side, right, I end up with cosine squared x minus sine squared x equals sine x. And you might be telling me, dude, you're trolling, you still have cosine, and I'm telling you, hold up. The IB loves when you use formulas from the formula booklet. There is something planned up ahead for us. So the moment you do this, now this formula looks friendly because this formula has the squares up there, the squared up there, right? And so this formula up here, you can rewrite it and leave cosine alone as cosine squared theta equals 1 minus sine squared theta. So all I really did was pass this guy to the right. Okay? That's all I did. And so once I apply that formula here, I end up with 1 minus sine squared x minus sine squared x equals sine x. And yes, this looks kind of nasty, but hey, look at that. We just got rid of cosine. So again, a lot of times, especially for show that exercises, people get scared because the final answer is super scary and it's super long and it's super hard and all this stuff. But at the end of the day, focus on the small things. You started with cosine and sine, you need to end up with only sine. So use all the formulas and all the tools you have to leave it as only sine. So once we did that, reaching what they asked for is much easier. So on the one hand, we have it equal to 0. And on the other hand, notice, you have a minus 1 and you have a positive for the sine squared. Okay, so we want to leave sine squared positive and have it equal to 0. Those are like the main things we have to do. So if I combine over here, I end up with 1 minus 2 sine squared x equals sine x. And so here, first thing equal to 0, but also keep the thing that's squared, right? I need to keep it positive. Right now it's negative. So here I'm going to go ahead and take the courage to do plus 2 sine squared x plus 2 sine squared x. So this makes me end up with 1 equals 2, here's a squared, sorry, sine squared x plus sine x. And when you have a negative 1, which makes sense because I do minus 1, I end up with 0 equals, and just to leave it as a show that, I end up with 2 sine squared x plus sine x minus 1 equals 0. So bada bim, bada boom. That is for part A. Not that hard. Just keep in mind the process. So with the show that exercise, you got to go from stuff with cosine and sine to stuff with only sine. So use all the tools you have. And this right here is very important. Know the tools you have. Study with the formula booklet. A lot of students don't do this as much as they should. So if you're listening to this video, whatever point in time it is, whether you have the exam in 30 minutes or 30 days or 2 hours, study with the formula booklet, get familiar with it, have it open next to you at all times. There's no reason not to. That is for part A. Then for part B, we have hence solve cosine 2x equals sine x where blah. Okay, and I know some of you might be thinking, what the heck is going on? So basically, on the one hand, it says hence. See, anytime the IB says hence, it's kind of just, it's a big hint that, okay, what you did in part A, you need it for part B. Okay, so having that in mind, what you got to do is, first I'm going to show you visually what's going on. See, before anything, here it's telling you the domain. All right, you guys, and domain is possible x values. And whenever it says solve, in this context, it's going to be for finding the x-intercepts. And so basically it's telling you graph this, right? Graph this and find the x-intercepts within this domain, right? Now, I'm going to go ahead and pull up Desmos, okay, just to show this more literally graphically. So if you graph it, it looks like this. Now here there are a lot of x-intercepts, right? There's this one, there's that one, there's this one, there's that one, there's so many, right? And so what they're telling you is that you need to find all the x-intercepts that are between negative pi and positive pi. So if I go back here, it's between negative pi and positive pi. Ah, so all you need to find are this one, and this one. And those are actually the answers. It's negative pi over 2, it's pi over 6, and it's 5 pi over 6. So this is just a bit of context of what we're doing and why we're doing it. Now, like any sine function, the cool thing about it is that it is an infinite cycle. It always looks the same. It always repeats. And so one of the main tools you have is that to visualize this more clearly, you can use the unit circle. And so because this is a repeating loop, so is the unit circle. It is also a repeating loop. And so the answers, the x-intercepts that we're looking for, are sort of hidden in the unit circle here. Okay? So that is the game plan. That is what's happening. That is the intuition behind the scenes. Now that we have that in mind, I'm going to show you the way to solve it, right? And so first things first, for part B, I'm using what I have from part A. So I need to solve this. Sine squared x plus sine x minus 1 equals 0. Now, because it equals 0, I mean, you're finding the x-intercepts because this thing equals 0, okay? That's the other thing I forgot to mention. You're finding the x-intercepts because this thing equals to 0. Now, from here, this should ring a bell. This should look a little bit familiar, and if you paid a little bit of attention in class, you might realize that this has to do with a quadratic. The IB loves to put quadratics hidden everywhere, okay? And here you have a quadratic because technically, if you go ahead, and this is something you do have to do, by the way, okay? Just to make it more friendly, technically, if you go ahead and call sine x, I don't know, let's call it m, okay? That means for this first part, I have 2m squared plus m minus 1 equals 0. And so, this makes a little bit more sense. So if I ask you to factor this, okay, if I ask you to factor this, find the x's, find whatever, see? Solving this is a lot more friendly, right? And so from here, there's two ways. So you can either do factoring, or you can do the quadratic formula. I'm going to use the quadratic formula just because, in my opinion, yes, it might take longer, but it always works, okay? Factoring is actually mega fast here, but I know some people just don't like factoring, so I'm going to show you the longer but more reliable way. So the quadratic formula looks like this. It looks like negative b plus or minus square root b squared minus 4ac divided by 2a. Now what is a, what is b, what is c? This is all in the context of a quadratic. So your a is whatever is in front of the x squared. Your b is whatever is next to x, and your c is whatever is alone. So in this context, a is going to be 2, b is going to be 1, because there's a hidden 1 here, and c is going to be negative 1, of course, right? So if you go ahead and plug all of this in, and remember the quadratic formula is for finding the x-intercepts, okay, so is factoring. From here you can end up with negative 1 plus or minus square root of b squared, so it's 1 squared, minus 4 times 2 times negative 1, divided by 2 times 2. So this ends up giving negative 1 plus or minus square root of 1 plus, so it's 4 times 2 times negative 1. So it's plus 8 divided by 4. So from here you end up with negative 1 plus or minus square root of 9 divided by 4, same as negative 1 plus or minus 3 divided by 4. And so from here you need to apply the plus or minus because you gotta do what you gotta do. So once you apply the plus or minus, all you're really doing is saying, okay, there's one answer that has a positive and one answer that starts with a negative, right? So for the positive, I have negative 1 plus 3 divided by 4, and for the other one, I have negative 1 minus 3 divided by 4. So over here, you end up with 2 over 4, and down here, you end up with negative 4 over 4. So that means for your answers, on the one hand, you have 1/2, and over here, you have negative 1, right? Now, these are the answers thinking for m, right? So technically, because you replaced m earlier, technically what you just found is that one of the solutions is that m equals 1/2, and the other solution is that m equals negative 1, which is the same as saying that your zeros are at 1/2, 0, and at negative 1, comma 0. Now, because I replaced for sine, you gotta replace back. So technically, and you have to do this for getting full credit, here, one of your solutions is at sine x 1/2, and your other solution is at sine x negative 1, okay? So here, I just found my x-intercepts for what I'm looking for, right? Now, because they put it in this domain, it can come in two different ways, okay? This is technically like an angle. See, I know we thought about it as domain, and visually it's very friendly to think about it as a domain. But in terms of the unit circle, which is the tool we have to use, this is really just an angle, okay? So angles can come as degrees, which is what we usually know, or as radians. And so follow the colors I just put. So degrees is going to be yellow, okay? Radians is going to be blue. And so in this image that I pulled up, okay, degrees is all these guys here. All of these are in degrees. It's usually what we face, okay? It's what normal people use. But sometimes radians is useful, okay? And so radians are here. Now radians and degrees are equivalent in their own way. What do I mean by this? For example, if you look at 30 degrees, okay, its equivalent is pi over 6. 120 degrees, its equivalent is 2 pi over 3 as radians, okay? And for 4 pi over 3, its equivalent is 240 degrees. And so, once we have that in mind, a very interesting thing happens that it's important to have clear, okay? Pi radians is 180. So pi radians equals 180 degrees, okay? So technically what they're asking for over here is the answers where you have negative 180 degrees up until x equals 180 degrees, okay? So these are saying the same thing. All right, that's just a bit of context because I know you've probably seen that somewhere, and I need you to understand that pi radians, okay, it's just pi radians equals 180. All right, that's what I'm trying to tell you. All right, anyways, so from here, how do I find my solutions? And so from here, you have some of your solutions, right? The thing is, you need to transpose your solutions onto the unit circle in order to get the answer. So one of my answers was sine x equals 1/2. Your other answer was that sine x equals negative 1. And so where is sine x equals 1/2 and where is sine x equals negative 1 in my unit circle? Guys, sine, cosine, tangent all have something associated to it. So sine and cosine and tangent is oftentimes called the famous so, ka, toa. What the heck does so, ka, toa mean? So is opposite over hypotenuse. Ka is adjacent over hypotenuse. And toa is opposite over adjacent. And so you can use this knowledge here to figure out your answers, okay? And so I know right now it might seem very weird what is happening, but I assure you it's gonna click in a moment, see? So the unit circle, why is it called the unit circle? Why is it unit circle? It's called unit circle because the radius it has equals 1. It equals 1 unit, see? So notice all these different key points that I'm putting now. So this 1 comma 0, this 0 comma 1, this negative 1 comma 0, this 0 comma negative 1, right? All of these have a radius of 1. So all of these lines that are actually drawing onto it have a distance equal to 1. All of these have a distance of 1, okay? All right, why is that useful to know? Because when you start thinking in terms of opposite over hypotenuse, well, all of these hypotenuses equal what? all those hypotenuses equal 1. Because the hypotenuse is the long part of your triangle. That is another thing I have to explain quickly. So your triangle, right? So you have a 90 degrees here. Your hypotenuse will always be this. Hypotenuse is always going to be the long side, period. Okay? So all of your hypotenuses equal to 1. So if you have sine x equals 1/2, that means that, thinking in SO, right? If the hypotenuse equals 1, then your only option is that the whole opposite equals 1/2. Now, what is opposite in this context? So, the sine is always going to be, or all these angles, better said, is always going to be in respects to this. See? So, for example, you have this triangle here. Okay? So here you're doing sine theta in respect to that. And so the hypotenuse equals 1. And the opposite is all of this. And so the opposite, notice, it's my height. Ah, it's my y value then. So here, the height of this, the opposite of this, is 1/2. Oh, damn. So the opposite of this guy, right, just to practice, so the opposite of this guy is -1/2. Interesting. Okay. So now that we have that in mind, and you walk into the test having the unit circle memorized, because it is something you have to do for this type of exercise, if you look at sine x equals 1/2, and you remember the SOHCAHTOA thing, and you say, okay, this guy on YouTube said all my hypotenuse is equal to 1 in the unit circle, so that means I need to look at, for sine, I need to look at the opposite, which is y values. Okay, so technically it's just y values. You gotta remember the unit circle and think, where do I have a y value of 1/2? Kapow, you have a y value of 1/2 here. Okay, so one of your answers, because it's in radians, is going to be pi over 6. So the first answer, let me just be very organized, see? So one of your first answers for sine x equals 1/2. One of your first answers, so I'm going to put x1, one of your first answers is pi over 6. Now let's not forget, we're always thinking between negative pi and pi. So the answer you just got, is it within that realm? Yes, it is, right? Pi over 6 is within that domain, see? So this is one of my answers for sure, okay? The other answer that you might have already noticed is that, okay, you have another y value that's 1/2. It's this one here. And so you say, okay, so my other answer is going to be 5 pi over 6. Now, I'm sure at least one of you out there is saying, dude, what the heck? I don't want to remember this whole unit circle. That is insane. And I will answer, yes, it's crazy. And you do need to memorize a part of it, but not everything. And so you can pass from this to this with simple logic. I told you guys way earlier that pi is how much in degrees? Pi is 180 degrees. And so basically, because the unit circle is filled with like mirrors and stuff, the angle pi over 6 here, the opposite of 1/2 here, is the same, if you think about it as a mirror, as the triangle over there. So how can you pass from one triangle to the other? Well, you can think about it as 180 degrees is this whole thing. So 180 minus this blue chunk here, right, makes you end up with the other side, okay? So basically, another way you can think about it is that you can do, if your first answer, the part you memorized, right? If your first answer was pi over 6, in order to find the other one, all you have to do is do pi, which is basically 180, so you're finding the other side, pi minus pi over 6. So for x2, you end up with, you amplify so that you can compare them, so it's 6 pi minus pi divided by 6. So your x2 is going to be 5 pi over 6. So all you really did is that you found your x1, okay, and you did minus pi to your x1. So you did, you did pi minus your x1. Sorry, so you do pi minus your x1. This gives you your x2. That is what I was trying to say. So if you do pi minus x1 for your x2, which is this line of math here, you can get the other side, okay? So again, you can either memorize the whole unit circle or memorize part of it and do the pi minus thing, okay? I suggest doing the pi minus thing, to each their own. So anyways, one of your solutions, as we said, is pi over 6. The other one we said was 5 pi over 6. Now, we're almost done, right? Because this is thinking about sine x equals 1/2. But the other answer that I got in my quadratic was sine x equals -1. So now we gotta go back to the unit circle and think about the scenario of sine x equals -1. So sine x equals -1, where would it be? Sine is for y values because it's the opposite, and hypotenuse equals 1. So where do I have a y value of -1? I only see 1. That was a lot of repeating. So it's right here. There's your y value of -1. There is no other. And so this one's a little bit more friendly. Basically, your answer for this one is 3 pi, or the x1 you got for this one. See, think about it that way. So the x1 you got for this one was 3 pi over 2. Now, is 3 pi over 2 one of my answers? Is it within my domain? It's not, because your domain goes from -pi over 2 pi. If you want to see it graphically, so my domain is enclosed by the blue and green, there is my 3 pi over 2. It is to the right of the green, so it's not within my domain, so you do not consider it. Now, because this is a cycle that repeats always, you can do pi minus this guy, and you end up with the same sort of intersect, but here, which is going to be -pi over 2. So visually, that's what we're doing. So you do pi minus this guy here, you're going to end up with the same answer, but over there, because it's a cycle that always repeats. That's why this works. So x1 gave you 3 pi over 2, which does not work, not within the domain, but your x2 for this solution is going to be pi minus x1. So it's going to be pi minus 3 pi over 2. You leave it all in the same sort of fraction denominator thing. So it's going to be 2 pi minus 3 pi divided by 2, which is just -pi over 2. And so your last answer is -pi over 2. So basically, if you're more rigorous in your approach or in how you express your answer, better said, you're going to be putting as your final answer, and this is what the answer key says, your x values are going to be -pi over 2, because you put them in order, right? Comma, pi over 6, comma, 5 pi over 6. All right? So that is how you solve this exercise. It's very important to keep in mind for this last part, for finding the other solutions, you do pi minus whatever you got. See? So you do pi minus whatever you got, and that helps you jump from this to this here. See? Technically, in other exercises, you actually need to add or subtract 2 pi, and all that really makes you do is jump all the way over to like another sort of cycle, okay? And so adding or subtracting 2 pi just lets you go from one cycle to the next. And depending on your domain, because I mean my domain could have been much bigger, right? It could have been 2 pi. That's when that trick helps. The adding or subtracting 2 pi in case your domain is bigger. In this case, we didn't need to do that, but I'll point it out anyways because, well, I mean, I'm sure some of you out there need to figure that out. See? And last but not least, I would like to make an observation. See? This last part was hard. This last part took a lot of time and took a lot of knowledge, and you needed to know about the unit circle and a bunch of stuff. See? So take a moment, look at the answer key. So looking at the answer key, well, part A is worth 1 point, and it's a lot of formulas and stuff, and you gotta know what's going on. See? So that is a hard point to get, in my opinion. But then for part B, it's worth 5 points. And 4 of the points, dude, it's crazy. 4 of the points is just doing the thing of the quadratic and finding the x values. Finding the initial solutions, right? But the whole thing about the unit circle and the sine and the cosine and all that stuff, is only worth 1 point. So I'm just pointing it out, you guys. Especially if you're low on time, do the part that is quick. Do the part that is just factoring and the quadratic, right? Think about it this way, you guys. This that I'm putting now in, let's say, light blue. See? So this that is in light blue, this is worth 4 points. And this that I'm putting in purple, this whole thing is worth 1 point. It's crazy. It's actually crazy. So if you have time, study with the mark scheme and notice what the IB gives more points of or less. Okay? Now, it could have been that this was worth, I don't know, 3 and this other one was worth 2. That can happen. Okay? It can happen. I feel like sometimes it's subjective. I'm not sure how they define it. I have no idea. But I'm just pointing it out, you guys. Do the quick part first. See? The part that is in light blue is something you should be able to practice and manage pretty quickly. And the part in purple, well, it's harder, and I'm sure sometimes it'll be worth maybe more than 1 point, but it's much more time consuming. Especially for a test. This is not just a test of math, you guys. It's also a test for your test taking skills. It's also a test with time. Your time is not infinite. It's not a lot, actually. So prioritize. Do the fast parts first, the hard part later, or the more consuming part later. See? All you care about is points. You don't care about answering everything perfectly. You care about getting the maximum amount of points, so use your time wisely. You should be answering at least a little bit on each question. Don't get stuck on the hard part and not end up doing other questions. See? I just want to point that out because I don't know, this isn't just a math channel, this is an IB channel. And I know you're going to be giving the May exams, the November exams, and I'd rather give all the tips and tricks I can. See? So keep that in mind, use your time wisely, and yeah, I hope it helped. Alright, you guys, and now for number 5, we need to find the range, okay, the range of possible values of k such that this has at least one real solution. So I know that for a fact, a lot of you look at this and you say, alright, next question. But there is one big hint here that once you start noticing is going to help you to answer all exercises similar to this one. And it has to do with the last couple buzzwords, which say that this thing has at least one real solution. And so, of our tools that have to do with amount of solutions, there is only one. And your tool, which is in your formula booklet, by the way, is what we call the discriminant. And so the discriminant of a quadratic equation is this guy here. And so notice, where does the discriminant come from? The discriminant, which is right there, comes from this right here. And so how do you interpret the discriminant? Anytime your discriminant is, for example, greater than 0, you have two solutions in your quadratic. If your discriminant is equal to 0, you have one solution. And if your discriminant is negative or below 0, then you have 0 solutions. Now, something I need to put a quick disclaimer here is that it's two real solutions. It's one real solution and it's 0 real solutions. Technically, you can have imaginary solutions, okay? And this has to do with imaginary numbers. I'm not gonna get into that, but basically, whenever you have a square root that is, for example, negative, you can solve it because I, your imaginary number, equals square roots of -1. And so through this, you can actually solve square roots of -4. I'm not going to show you because it doesn't really matter for this, but that is why here it says one real solution, okay? It's not asking you to go into the realm of imaginary numbers and crazy stuff. It's just asking for you to find the discriminant when it is greater than or equal to 0. Why greater than or equal to 0? Well, we said that greater than 0 was for 2 solutions. We said that equal to 0 was for 1 solution. And so if it's at least 1, then it is either 0 or greater. So discriminant has to be greater than or equal to 0. So awesome. We just identified that we need to use the discriminant and that is the way to go, and you're going to find the discriminant when it's greater than or equal to 0. But you're probably looking at this and telling yourself, how the heck is this going to be a quadratic? This does not look like a quadratic. What is this guy on YouTube trying to tell me? And so generally, you shouldn't trust people online, but just for today, you can trust me, okay? And so from here, once you identify the thing of the discriminant and that you want to try to reach something that looks like this, because this is where the discriminant comes from, it comes from a quadratic, right? Once you identify that, try to reach that, okay? And so for using the discriminant, it's also important, notice here, that they equal it to 0. Whoops, it's not letting me highlight what I want. For the discriminant, you need to equal it to 0. Okay, once you equal it to 0, you can use this guy here, you can use this guy there. I mean, it's not that you need to equal it to 0, but for our intents and purposes, for reaching what I haven't read, let's try to do that. Leave 0 on one side, okay? And so notice, your quadratic, its first term has an x that is squared. Its second term does have an x, but it's only to the power of 1. And your last term does not have an x. So if I try to replicate that, I can do minus 3e to the power of x to both sides. I end up with e to the power of 2x minus 3e to the power of x plus ln k. And this, believe it or not, is a quadratic. Now, I really want to explain why. See? So notice, a quadratic, as I said, its first term has something squared for x. Here is your squared x, okay? The 2x on top. For bx, you only have x, like 1 times x, right? So it's legit, right? And this last one does not have an x, so that is your c, okay? All right, I know this might be a little bit hard to like visualize or imagine, so another way that I can help explain it to you is imagine you're substituting just for a second, I don't know, that big A equals e to the power of x, okay? So if big A equals e to the power of x, that means this first term ends up as a squared. Because if you square both sides here, you end up with a squared equals e to the power of 2x. Ah, okay. So that means this first term can be rewritten as a squared minus 3. Oh yeah, so a is e to the power of x minus 3a plus ln k. This looks more like a quadratic now, doesn't it? But really, it's the same as this. All I did was replace big A for e to the power of x to make it easier to visualize it. Okay, but really, this is still a quadratic. So guys, I think the hardest part of this exercise is what I just explained, is realizing that when they say one real solution, you gotta be thinking immediately in terms of discriminant. And if you're thinking in terms of discriminant, you are in the realm of quadratic equations. So try to find the quadratic equation, as crazy as it might seem. And in this case, it was staring at us this whole time. And so from this step here, you can go ahead and define little a, little b, and little c. Okay, remember that this comes from ax squared plus bx plus c. And so little a is what's in front of x squared. So in front of my x squared, in this case a, we have a 1 times a. So little a is going to be 1. For this next part, we have minus 3 for b. And for this next part, as crazy as it is, your c is ln k. After all, ln k is just a number. And so from here, you can use the discriminant, right? And so the discriminant, we said, and from the formula booklet we know, it's going to be b squared minus 4ac. So first, let's find out what my discriminant is, and then let's apply this thing here, the greater than or equal to 0, because we're talking about at least one real solution. So first, let's solve for the discriminant. So if you go ahead and plug in, you end up with b squared is negative 3 squared minus 4 times a, which is 1, times c, which is ln k. And so all of this equals your discriminant, okay? So your discriminant ends up being 9, because negative 3 times 3, minus 4 ln k. All right, interesting. And so from here, we need to apply our condition, which is the discriminant being greater than or equal to 0. So this whole thing has to be greater than or equal to 0. And so because we want to find the values of k, try to get k alone. So from here, what I would do, there's a couple different ways, but what I would do is just plus 4 ln k to both sides. That way you get k a little more alone, right? So this goes away with this. You end up with 9 being greater than or equal to 4 ln k. You want to keep getting k alone, so you can divide by 4, divide by 4. You end up with 9 over 4 is greater than or equal to ln k. Now, just because for me it's easier to visualize it, I'm going to flip it for a second. So ln k is less than or equal to 9 over 4. See? And from here, we're pretty much at the last step. And so from here, you need to find the value for k. You already got k alone as much as you can. And the last step is a little bit creative. Okay, you have to be familiar with logs and stuff like that. And so because we need to be familiar with logs, let's go to my formula booklet and look for logs. Oh, it's actually just right there. So as you can see here, first things first, the exponential function and the logarithmic functions are like inverse of each other. See? So for example, in math, you have plus and then you have minus. You also have multiply and then you have divide. Like all of these are opposites, right? And so you also have the exponential function and the logarithmic functions. Okay, those are also opposites. And so how do you like read the logs? Well, this is actually how the exponential function interacts with the logarithmic function. But technically the definition of log, I hope it's here, else I'll just give it to you, but logarithmic, is there really not the definition of log here? Wow, that's crazy. Well, you learn something new every day. Oh, there it is. Okay. So here, sorry about that. This is the definition of log. What I showed earlier, I'm going to leave it in the video because it's still relevant. It's how the exponent function interacts with the logarithmic function. But this is like the hardcore definition of log. See? So notice here. Basically what's happening, start from this side. Okay? Start from this side. So basically, what you ask your logarithmic function is your base to the power of something gives you what's in parentheses. Your base to the power of something gives you that parentheses. It's the same thing, okay? And so if I go over here, your base, what is your base here? It's natural log. And natural log always has a base of e. Normal log always has a base of a. I mean, damn, sorry. Normal log has a base of 10, unless they tell you otherwise, okay? If they tell you otherwise, you have a different base. But the standard, the default, is that natural log has a base of e, log 10 has a base of 10. And so here you're asking, like this whole thing basically, is that e to power of something, something is on the other side, right? It's on the other side. So e to the power of that something, 9 over 4, has to equal k. Ah, okay. So now we're getting somewhere. And so this now gave me like how far k can go, okay? If k goes anywhere beyond this, it stops working, but anywhere less than this, it's okay, see? How do I know this? Because ln k has to be less than or equal to 9 over 4. And so, because it has to be less than 9 over 4, then k can go as far as 9 over 4. All right, awesome. And so, for writing down the range, well, ln k in this function here, it's inside a logarithm. And so something that I didn't tell you earlier, but I tell you now, is that the logarithm, the value that's inside, has to be positive. And so whatever's inside has to be positive. And so now, for example, if I pull up a quick graph on Desmos, just so you can see it, here I'm graphing ln of x. notice how the inside, my x values, I don't have a single negative x value. I have negative y values, yes, but there's not a single negative x value, okay? Because what's inside my parentheses has to be positive. And so that immediately tells me that k, okay, k has to be greater than 0. And I just found out from down here that this is the maximum value that that k can take. So k has to be greater than 0, and also it has to be less than or equal to e to the power of 9 over 4. And that, ladies and gentlemen, is how you do number 5. So again, I don't think it's incredibly hard, but the hardest part, for me at least, is realizing you have to use discriminants. Now, I've also realized, because I've done a couple of these tests already, is that the thing, when it says has at least one real solution, it's a massive buzzword, okay? It's a massive hint that you need to use discriminant. So whenever you read at least one real solution, or at least two real solutions, or even no real solutions, whenever it talks about solutions, bada bim, bada boom, you're talking about discriminants, you're talking about the quadratic function. Try to find the quadratic function. I know it can be hard to visualize, so substituting can be a very good idea. Ladies and gentlemen, that is number 5, and I hope it helped. Alright, you guys, for number 6, it's not incredibly hard, but it is incredibly specific. So if you keep in mind one or two things that have to do with the sinusoidal functions or the sinusoidal exercises, I think you'll be good to go, okay? And so a lot of these is just context. If you understand it well, you're good to go. If you've never seen or never reviewed the sine function, there's not much I can do to help you because not even the formula booklet has a lot of tips and tricks here. This is stuff you just kind of have to know, okay? So just a heads up, it's not that hard, but it is very specific, okay? So, number 6. The function f is defined by f of x equals sine qx, which is this guy that you're looking at here. They tell you that q, the guy inside of the parentheses for sine, is positive, okay? The following diagram shows part of the graph of f for these values here. Now, what the heck does this even mean? Well, because there's an x in between it, it's basically telling you, dude, your x values go from 0 up until 4m, which is why in your graph you go from 0 up until 4m, okay? And so that is how far your x values can go, and that also affects your y values, right? Because you can't have an x equals 5m, you don't actually have a point here for y, see? So that is what they define as domain. And so let's just recall that for a second. Domain is technically your possible x values, okay? Well, range, you guessed it, is also your possible something, but in this case, your possible y values, okay? So your domain is possible x values, your range is possible y values. Here they define your domain. They also mentioned that x is in radians. Now, what the heck are radians? Radians, whoops, apparently radians is a powerful word. So radians is just a way to express degrees. All right, so let me just give you an example. It'll make a little bit more sense. 2 pi radians, okay, so 2 pi radians equals 360 degrees, while 1 pi radian equals 180 degrees. It might make a little bit it might make a little bit more sense if you look at a unit circle graph. So in Google you're gonna find, sorry I had to cough for a second. So in Google you're gonna find a lot of different unit circles. And so for example here, right, you have that for 90 degrees its equivalent in radians is pi over 2. For 270 degrees, its equivalent is 3 pi over 2 radians, all right? And as I said, 180 degrees has a single pi next to it, okay? So that means if you went all around, again with 180, you need to do pi plus pi, you end up with the 2 pi I mentioned here, see? So everyone chill out, chillax. Radians is just a way to express angles,
okay? And why can this be useful? Because, well, once you memorize the unit circle, which you should for the test, it is an amazing tool which helps for a lot of the steps you're about to see, okay? Anyways, blah, blah, blah. There are x-intercepts at x equals 0, at 2m, and at 4m, okay? So for part A, we need to find an expression for m in terms of q. So first things first, when they say m in terms of q, what this is really telling you is that they need m to be alone. I'm going to be very clear on that. When they say m in terms of q, it means that m is alone, and you're going to end up with a bunch of q's on the other side doing a bunch of different stuff. Maybe it's 2q, maybe it's q plus 7, whatever, okay? M has to be alone, and on the other side, the only variable you can have is q. And so the classic would be y in terms of x. And so an example of y in terms of x would be y equals, because y has to be alone, y equals, I don't know, ax squared plus bx plus c, right? Well, actually, in terms of just x, I could not have a, b, or c. Maybe that wasn't the best example. You would end up with, I don't know, 7x squared plus 4x plus 5. And so, yes, you end up with a lot of different terms, but what would be the only variable? Your only variable is x. You do have a bunch of different x's, but only x. There isn't a, there isn't b, there isn't c. It's only x. So that is what it means when it says m in terms of q. M has to be alone, and you will end up with only q's on the other side. Now, to further understand how to solve this, you first need to identify where q is. And so q is inside the parentheses of sine. Now, if you don't know much about sinusoidal functions, or you didn't review in time or whatever, that is useless information to you. So let me give you a quick review for how sine functions work, okay? Technically, a sine function, all right, so I'm just going to write it over here. Technically, a sine function will have 4 different key values, okay? You have a, you have b, you have c, you have d. And so technically, your sine function, I'm just going to put sine, I don't know, sine x, okay? A, B, C, and D, enter it in various different ways, all right? On the one hand, you can have an A that is multiplying right outside. Now, A is easier to remember. A will be associated to amplitude, okay? What is your amplitude? Your amplitude is in your sine function, right? For example, here. In your sine function, your amplitude will be how high or low it goes in respect to the x-axis. And so an amplitude here, for example, from here to here, and let's say that this is 0, and then this is, I don't know, 2, and down here would have to be -2, right? And so your amplitude here would be equal to 2, just as an example, okay? The other thing that can happen, all right, is this b. So this b is going to enter inside the parentheses. So your b that I'm about to explain now and explain what it does, the b is the q. All right, so like b equals q in the explanation I'm about to do. Okay, so what is b? Well, b has to multiply x inside the parentheses, and there's not too much of a clear definition I can give you, but b is like associated to the period. I'm not saying that it is the period, but it's associated to the period. Why is it associated to the period? Because the formula for period, and this is very important, this is not in the formula booklet, write it down. The formula for period is 2 pi divided by b. This is in radians, by the way. If you want to have it in degrees, you can say 360, as I taught earlier, divided by b. All right, so the period, b is heavily associated to the period. It helps you a lot to find it, okay? And so this is a massive hint for how to, find Q in our exercise, but for now, let's move on. B is just sort of associated to the period, right? Think about it this way. If you have a B that is bigger, that means your function is doing repetitions more quickly, right? So this is a bigger B, all right? And a smaller b, like less than 1, means that your repetitions are a little bit longer than before, okay? And so that's the idea. A b that is less than 1 would look something like this, and a b that is greater than 1 would like do its repetitions more quickly, right? That's the main idea I'm trying to tell you guys. Yeah. What else? So c, technically c, would be something like this. C, I don't see it show up too often, I'll be honest. But technically C is something that is adding or subtracting inside and is what we're going to call a horizontal translation. How can you memorize this more easily? Well, notice that it is adding or subtracting directly to x. And x is associated to your horizontal values because in your xy axis, your x is horizontal. So whatever is adding or subtracting specifically to x will be a translation to the left or right, okay? And last but not least, for D, you guessed it, it's going to be the vertical translation, okay? And so you might be thinking already, well, if I look at my function here, I have sine parentheses qx, right? And so sine parentheses qx, does it have a horizontal translation? Does it have a vertical translation? And technically, I would say yes, but it equals 0. And even for amplitude, it does have an amplitude. Like, what is multiplying sine qx right now on the outside? A 1. There is a 1 hidden right here. And so your amplitude is equal to 1, which is why from here to here, the distance is 1. Ah, look at that. That's why the distance from here to here is of 1. And the vertical translation, the plus d that is like outside, well, here I have a plus 0, right? You have a plus 0, which makes sense because if you look at the like the line that cuts through your sine, it's actually at y equals 0. So I'm just saying, you guys, that is the context of the stuff that can show up, and more often than not, what you end up using the most in my experience is what I told you for the formula of the period. Okay, so let's go back down here. Let's see how that plays out for our exercise. And so you want to find m in terms of q, and you know that q is associated to the period. So immediately you can already say, right, you can already say for part A that the period equals 2 pi divided by b. And you know that b, from the function that they gave you, sine qx, you know that b is whatever multiplies x inside the parentheses, so period has to equal 2 pi divided by q. All right, now we're getting somewhere. Now we just need to find whatever period is, okay? And so period, I vaguely defined it earlier as like, it sort of affects like how fast or slow you do like these repetitions on your sine function. But maybe a better way to put it, or how I like to, remember it, okay, is that your period is like the distance from max to max. So period is the distance from max to max. Now this is the hardcore definition, but this actually has a bunch of different implications I'm about to show you. And so from max to max, well, if I were to keep graphing this, right, following the pattern that I see, I would need to have a maximum over here, right? And then it would cross again over there, right? And so from max to max, you can think about, so it's from here to here, this is a period, right? And so this is going to be one period from max to max. So you're thinking it's 5m minus 4m. So 5m minus, 5m minus m gives you 4m. I gave the answer out loud. So 5m minus m gives you 4m. So the period over here we're going to call 4m. So 4m equals 2 pi divided by q. Now before we move on with the math, let me explain why knowing the period can be very useful. And so the period, as I said, is the distance from max to max. But technically, depending on the exercise, it can also be useful to think about it as the distance from the minimum to the minimum. After all, it's the same, right? If you compare the max to max, it's the same as if you compare from the min to min. And the other cool thing that you can start considering, and I know this is going to be a little bit trippy, but it's very useful to know, okay, is that imagine this red line that I drew, okay? So this red line that I drew, that goes like this for a period. Imagine you shift it to the left little by little. So if you shift it to the left little by little, on the one hand, you would end up with something that goes, I don't know, like this. Then you go with something that ends up a little bit like this. And lo and behold, eventually, damn, you end up with something that looks like this. Something that is touching the x-intercepts. Ooh la la, that seems incredibly useful. Maybe not now, maybe for later. And so thinking about the period can be a massive hint. Now, here, technically, it gives you the x-intercept of 0 and the 4m, and there's also one in the middle for 2m. So you gotta watch out for that kind of detail. But you know for sure, the period also helps you find the x-intercepts because the sine function, it goes on like this forever. And so any sort of proportion that you find from here to here, or from, I don't know, there to there, or even from, you know, like from here to here, is something that plays along the whole graph all the time. And so the period distance, it's a cycle that repeats, can be useful to know to find all these different sort of values. The last thing I'm going to tell you, just because the IB loves to, do exercises like this, is that technically here, they didn't give you the other maximum, right? I mean, I drew it and it was very easy to spot what the period had to be, but imagine you didn't spot it. What could you have done? Well, the period, as you can see here, as I said, it's from max to max, but you can also think about it as like, if a period is a distance from max to max, you can also think about it as twice the distance of max to min. And so if you take the distance from max to min, which is usually what they give you actually, just like half a cycle or whatever. So if you think about from max to min, this distance is 3m minus m, it's 2m. But this times 2, you know for a fact has to give you the other max. So 2m times 2 gives you 4m. Okay, so that is another way to find the period. You take the distance from the max to a min and multiply by 2. All right. Why does this work? As I said, the sine function repeats forever, so all these different properties really start to shine. All right. All right, that's a lot of blah blah, but sometimes you need blah blah in your life, especially for math. So, yeah, deal with it. Anyways, here we are, and here we are almost done. And so you want m in terms of q. That means that m has to be alone. So m has to be alone. How do you get m alone from here? Well, it's being multiplied by 4, so you can divide by 4 to both sides. So that means this goes away with this. M has to equal 2 pi divided by 4q. You divide by 2 on the top and on the bottom. M, whoops, that looks like a very nasty M. So M has to equal pi divided by 2q. So let me put this in light blue just so that we recall what's going on. M has to equal pi divided by 2q, and that is for part A. Then they tell us that the function g is defined by g of x equals 3 times sine, and then parentheses 2 over 3 times q times x. For a new domain, so interesting, so now your function reaches a little bit more. Instead of reaching 4m, it's going to reach 6m. And on the axis above, you need to sketch the graph of g. Now guys, I'm going to mention something right away. Yes, it's a sketch problem, and you might be thinking, haha, easy points, but it's worth 4 points. And so sketching is not only about nailing the visual aspect of how it should look like, it's also nailing what I'm going to consider like key points / aspects, okay? And I'm just going to leave this clear right away because I feel like a lot of people miss points on sketching just because they don't understand that, dude, it's not just about it looking nice, it's about it being accurate and putting the key points and the key aspects. So let me actually show you the answer key for a second. Over here you can see that the 4 points that show up is on the one hand that the scale factor is seen anywhere. So that this is like the part of like it looking it nice. But then you need to be accurate on the amplitude. Then you need to be accurate on the domain. Then you need to be accurate on the max and min and x-intercepts. And so again, this up here is like looks nice, right? But the majority of points is like that it's actually accurate, okay? So careful, you guys. It's not just about drawing anything. It's about drawing stuff that is actually accurate. These points that they're putting here, right, are not just any points. It's the max and min. It's the x-intercepts. And we're about to find out how to get those specific points with certainty, all right? So the main idea we have to like follow through with is that they're asking you to sketch something which looked similar to f of x. So how did f of x look? They gave us that f of x was sine qx. And now they gave us g of x, which is 3 sine parentheses 2qx divided by 3. And so think about it for a second. What is happening here? Well, on the one hand, my amplitude used to be 1, and now it passed to be 3. So that's the first thing I need to observe for part B. The amplitude, remember that amplitude is whatever is in front of your sign, right? So your amplitude now is going to be 3. So first thing first, amplitude equals 3. The other thing you can observe is that now your period is not just q, it is 2q divided by 3. And so your new b, which is going to affect your period, it has to be 2q divided by 3. Before your b was just q, now it's 2 over 3q. Everything else is the same. And so you have a new amplitude, and you have a new b, and you just see how this affects your max, your min, and all that stuff, right? Now, I did tell you guys earlier that if your b is greater than 1, your frequencies happen like faster, right? And if your b is less than 1, but also positive, I forgot to mention this, less than 1, but also positive, you end up with a period that like takes longer to happen, right? And so from here, your new b is 2 over 3. So that is a little bit less than 1, but it's still positive, and so your period will take longer to occur. Okay, so that means this maximum here is probably going to be, I don't know, somewhere over there. Okay, so it's going to take longer to occur the maximum and longer to occur also the minimum. Okay, and so everything is going to be like a little bit more delayed, if you want to think about it that way, because your value for b is less than 1 compared to before. See, I mean it's less. Okay, it's less. All right, anyways, so I think the most important thing that you can do is always going to be apply the period formula. And so you apply the period formula from here. The new period, so let me just go like this for a second. So the new period has to be, well, you don't figure it out yet, right? And so the new period, well, we're going to put period equals 2 pi divided by b. Now b, we said was 2q divided by 3. And from here, you're working with fractions in a very nasty way. What I suggest that you do is that this numerator, you can put it as 2 pi divided by 1, and on the bottom you leave it as 2q divided by 3. All right? I like to think about it this way because technically from here, you can say, so because this is like a big division symbol here, you can think about it as 2 pi over 1 being divided by 2q over 3. And when they divide like this, you end up with 2 pi over 1 times the reciprocal, 3 over 2q. And so 2 pi is going to multiply 3, and 1 is going to multiply 2q. All right? This is just how you handle big fractions. Now notice, here's something interesting. The last, and this is like a math tip, okay? So the last step you reach is 2 pi times 3 and 1 times 2q. And so something very visually appealing when you have big fractions like this is that the 2 pi times 3 up top are the extremes multiplying each other. while the 1 times 2q are the ones in the middle multiplying each other. Interesting. And so you can just do like the edges times the edges and the inners times the inners, and you get the same result. And so that's how I like to do it. I think about the edges times edges and the inners times inners for big fractions, okay? Whatever, to each their own, see? Point is, you're going to end up with 6 pi divided by 2q. And so period, right? Let me just be a little bit more organized in my approach. So period, as I was saying, has to equal 6 pi divided by 2q. Now you can divide by 2 on the top and on the bottom, and so period has to equal 3 pi divided by q. Now, q is a little bit hard to read, and it's actually not that useful. It would actually be more convenient if you replaced q with something that you can read. For example, m. Your whole x-axis is detailed with a bunch of m's. And so if you put this in terms of m, it's actually going to be a little bit more friendly to be able to read. And so lo and behold, what you need in part B comes from something you did in part A. So from this here, from part A, you can get q alone. And so you can do 2mq equals pi, right? If you multiply 2q to both sides. So this goes away with this. And if you get q alone, you can say that q has to equal pi divided by 2m. And so on. Now this, I can plug it in over here. And you end up with 3 pi divided by pi divided by 2m. And here I do the big fraction tip. So 3 pi divided by 1 divided by pi divided by 2m. I do the extremes multiplying each other, so it's 3 pi times 2m divided by 1 times pi, so just pi. Now because it's all being multiplied, this goes away with this, and the period, period finally becomes into something more readable. Period has to equal 6m. Okay, so your period is 6m, and this already gives you a whole point, okay? Now remember how I mentioned earlier that the period, you can think about it as max to max, right? Or you can think about it as min to min, right? You can also think about it as from min to min. Well, you can also think about it as, the actual math definition is max to max or min to min, but you can also think about it as x-intercept to x-intercept, right? Because it's all sort of parallel in a certain way. And so from here, what you can say, technically, right, is that because your period is 6m, right, you need to have an x-intercept here, right? So if you have an x-intercept here, you also have one over there. Now, you know for a fact you have one over here, and this is important, right, for the implication I'm doing. You know you have one over here because there wasn't any horizontal translation. If there would have been a horizontal translation, your first x-intercept of equal to 0 would have shifted, right? If you had a horizontal translation a little bit to the right, then your new graph would have had a different x-intercept. But because there wasn't any horizontal translation, you know for a fact, this is the right way to think about it, you know for a fact you have an x-intercept here because there was no horizontal translation. Because of the new period, you know for a fact there has to be an x-intercept all the way over here because this point repeats in 6m again, and that would be over there. That's the idea of the period. Like if your period is 6m, whichever point you look at, its height will repeat in 6m more units, or in that period amount of units, okay? So if you have an x-intercept at 0 and the period is 6m, you need to have an x-intercept at 0 plus the period, so 0 plus 6m, right? Just going to be 6m. All right, enough blah blah. That is one way you can identify some of the x-intercepts you need. So starting from there, we have something, right? The other thing we need to acknowledge, right? And so the other thing we need to acknowledge is trying to find which, like, is the x value, okay, of my maximums and minimums, okay, which is also going to be a big hint to see if you have another x-intercept in between. And so right now, for example, in the original one, you knew that the amplitude was 1, and so all the maximums and minimums had to be at a height of 1 or -1, right? For a fact. And so from here, well, you know that the amplitude is 3. And there wasn't a vertical translation, so the maximum or minimum only depends on the amplitude, right? If there would have been a vertical translation up here of like +1, and then another amplitude change, then yeah, you would need to consider like a different sort of approach. But right now, the only thing affecting my maximum y value is the amplitude that like appeared. And so because the amplitude over here equals 3, that means that your maximums for this new graph are going to be at 3 for a fact, or they're going to be at, for the minimum, at -3. All right, and now we're getting somewhere, right? And so basically what you can do from here is that you can say, okay, so I want to find the x value of the maximum, right? And so you know the maximum is somewhere at y equals 3, right? And so if you plug in y equals 3, you're going to be asking your function, where is my maximum, right? So if you take g of x, so you know that g of x is, you know, maybe something with more space. So you know that g of x from the exercise is 3 sine 3 times sine 2qx divided by 3. And so the moment you plug in 3 for g of x, you're plugging in the y equals 3 I mentioned earlier. And so you're asking your function, when y is 3, what is x? Okay, and the moment you find your x value is the moment we can really plug in like the maximum point with more accurate description. Okay, so that is what we're trying to do. You're trying to find the exact x and y coordinates of your maximum. So if you plug in 3 for y from here, you can end up with 3 equals 3 sine 2qx divided by 3, right? Now from here, you want to get your x value alone, right? Or leave it into something a little bit more readable. So first things first, you can divide both sides by 3. So you end up with 1 equals sine parentheses 2qx divided, all of this divided by 3, right? Now, the most annoying thing from this step right now is that you have a sign going around. So guys, how do you get rid of sine? What is the opposite of sine? The opposite of sine is sine inverse. So if you do sine inverse to both sides, you're going to end up with this going away with this, and so sine inverse, sine inverse of 1 is going to equal 2qx divided by 3, all right? And here's something I need to mention, like more from a conceptual stand of view. Whenever you do sine of something, as you can see, you get rid of sine and end up with only what's in the parentheses. But there's something I need to like point out that's very important, okay? Whenever you use sine, and this actually does show up a little bit here from the booklet, so just as an example, whenever you use sine, remember, or look, it's always like sine theta, right? And so what is theta? Theta is a way to express angle, okay? And so theta is an angle. The sine always has sine, like whatever's inside the sine, this is what I'm trying to tell you. Whatever's inside the sine is an angle, yeah? And so from here, when you do sine inverse, you end up with just the angle of 1. And so basically, this right here, although it sounds kind of crazy, is trying to, it's asking like, what is the angle at sine of 1? That is what it's asking for. What is the angle at sine of 1? And angle in terms of radians, because this whole exercise has been done in radians, okay? And so that is a weird question to ask, but that is why earlier I said, dude, if you know the unit circle, you're good to go. And so sine, right, we have associated sine and cosine and tangent to the famous so, ka, SOHCAHTOA. And so SOHCAHTOA, the SO is telling you opposite over hypotenuse, the CHA is telling you adjacent over hypotenuse, and the TOA is telling you opposite over adjacent. And so your unit circle is actually filled with a bunch of different triangles. See? So actually, if you go ahead and draw the unit circle just for a second here, right? So if you draw the unit circle just for a second here, you're going to notice that there's a bunch of different triangles that show up in all these different sort of key angles that they're throwing at you. And there's one key thing you have to acknowledge. The unit circle, what dimensions does it have? What dimensions does it have? This point here is 1, 0. This point here is 0, -1. This one is 0, 1. Sorry, that could not have been more wrong. This point here is -1, 0. And wow, I'm on a roll today. This one is 0, 1. Okay, so this one is 1, 0. This one is 0, 1. This one is -1, 0. And this last one is 0, -1. Okay, that makes more sense. And so from here, you're telling me that the radius is equal to 1. In all of these, the radius equals to 1. In all of these key different triangles that they're throwing at you, the radius equals 1. So all of these hypotenuses are equal to 1. Right, that's interesting. And so when you have a sign of 1, well, the hypotenuse equals 1. And so all this is really telling you is that the opposite equals 1. And what is the opposite in all of these triangles? The opposite of all of these triangles for a sign that's going over here, well, the hypotenuse is 1. And the opposite will always be, because it's the vertical like sort of growth, the opposite will always be the y value. So you gotta go to your, what this is telling you is go to the unit circle and find the y value that equals 1. And so the y value that equals 1 is this guy up here. And what is the radian associated to it? Pi divided by 2. That is what sine inverse is doing. Okay, that is what it's doing. And so from here, well, basically, this whole thing on the left is just going to turn into pi divided by 2 equals 2qx divided by 3. Now from here, get x alone. And I know we have a q going around, but I'll explain how we handle that in a second. Just for now, okay, get x alone, see? And so the first thing I would suggest that you do is that you can multiply by 3 to both sides, okay? So you multiply by 3 to both sides, this goes away with this, you end up with 3 pi divided by 2 equals 2qx. So from here, you can divide by 2q to both sides. That means you end up with 3 pi divided by 4q equals x. Now, this is not a good enough x value for us to read because our thing isn't, our x-axis is only in terms of m. It does not have a q in between, so it's very, very weird and confusing. But lo and behold, once again, part B needs something from part A. And so earlier we said that q can be written as pi divided by 2m. So we're going to do that once again. So q equals pi divided by 2m. That means that over here you end up with 3 pi divided by 4 times pi divided by 2m. All of this equals x. So let me simplify what's on the bottom first. So you end up with 3 pi divided by 1 divided by, this goes away with this, you end up with 2 pi divided by m. So all of this equals x. You can multiply the edges with the edges. So it's 3 pi times n gives you 3 pi m. And then the inner with the inner is 1 times 2 pi, so it's going to be 2 pi. All of these equals x. You can divide or get rid of pi on the top or the bottom. So x equals 3m divided by 2. And this, ladies and gentlemen, let's recall, comes from the fact that at some point, where is it? Here. That at some point, you plugged in 3 for y. So you were asking your function, yo, when y is 3, what is x? And why did we choose 3? Because the new amplitude from here was 3, right? So the new amplitude was 3. So that means the maximum has to be at y of 3 and then x of, as I discovered, and then x of 3m divided by 2. And so at 3m divided by 2, so 3m divided by 2 is the same as 1.5m, right? And so 1.5m, which is right around here, is where you're going to have your maximum, okay? So boom, we finally got 1 over key points. But from here, everything is just kind of like smooth sailing. And so from here, that means that my function for g of x is going to look initially like this, okay? And now we need to see where it might touch, like for the x-axis, right? Now, to further understand that, let's take the following idea. From 0, in the original one, right, the black line, from 0 to m, you first reach the maximum, and then you would add another m, right? So from the distance from 0 to your max, you add this distance again in order to reach the x-axis, right? And so if you take this 1.5m and you add that distance again, right? So this adding itself again, you end up at 3m. And so at 3m, you need to have one of your x-intercepts. And so, okay. So that means that for g of x, you have your maximum here. Then you cross the x-intercept over there. And then you add another 1.5, right? So you add another 1.5, that means you end up at 4.5. So at 4.5 is when you're touching for your minimum. Because as we said, that max and minimum have to be at 3. And all the process we just did was for finding the corresponding x values. See, so over here, I'm going to go ahead and write 4.5m, okay? That means I have a minimum, over here. And if you continue with this logic, lo and behold, you're going to end up with an x-intercept right there. So ladies and gentlemen, that is the appropriate way for graphing and sketching for number 6. I don't think it's incredibly hard, but you do need to be very conscious of the different tools, and especially the tools that are not in the formula booklet. I think understanding the context of what A, B, C, and D does is massively important, and just as a hint, I've seen that it's extremely important for you to know well the formula for period, okay? Know the formula for period, you pretty much always have to use it, okay? Ladies and gentlemen, that is how you do number 6, and I hope it helped.
Alright, you guys, and so now for number 7, well, we just start with section B, and for number 7, we have the function h. And so this function h is defined by h of x equals this whole thing. For x pertaining to all real numbers. That is what this is telling here. So x pertains to all real numbers. That means that everything in between you have, I don't know, you have -1, you have -1.05, you have everything in between, okay? Alright guys, so blah blah blah, they tell you that it has a local minimum at point A. So this is a massive sort of hint when we're talking about a minimum. We'll see how that comes into play later. That being said, for part A, you need to find the value of the y-intercept. So the value of the y-intercept, I'm sure that some of you can look at this and immediately say, lol, yes, this is y equals 3. Or this is 0.3. And a lot of you have that intuition because it is what doesn't have x next to it. And so you have h of x equals 2x times e to the power of x plus 3. And you say the y-intercept is 3 because it's the only one that doesn't have an x. And I would say, yes, you are right, but let's also understand why. And actually, you need to do this for a method point. Just putting this gives you 1 point. For the other point, you need to use the method. So you probably have this intuition because you've been taught that the quadratic formula, this c, okay, this c is the y-intercept. You were probably taught this and you never forgot it, but maybe you didn't understand why. And so the y-intercept, what do all of these points have in common? So all of these are y-intercepts, but what do they all have in common? For example, this one is 0, negative whatever, 4. This one is 0, 10. Okay, I'm just making numbers up. See, this one is 0, comma 12. What do they all have in common? Ah, all y-intercepts have an x of 0. And so whenever, ladies and gentlemen, you are trying to find a y-intercept, you just need to plug in an x of 0. So let me write that up here real quick. Basically, for x-intercepts, it's always going to be some x, comma 0. And for y-intercepts, it's always going to be 0, comma some y. And so for y-intercepts, you need to plug in 0 for x. And for x-intercepts, you need to plug in 0 for y. And with this golden rule, you can find all the intercepts you ever need in your whole life of math. And so for part A, because it's a y-intercept, we need to be plugging in 0, comma y. So if you plug in 0, comma y, well, this whole thing is y, so this whole thing is just going to stay as y. And y is going to equal 2 times 0 times e to the power of 0 plus 3. And so because this first term is times 0, it's just going to be 0 plus 3. So that is why y equals 3. And basically what this is telling you is that you have the point 0, comma 3. All right. So that was just a small and quick explanation for how to find intercepts. Okay. So for part A, it's just going to be 0, comma 3. For part B, they tell you to find this. And so this, ladies and gentlemen, well, tell me what it is. Two things could have come to your mind. Well, technically three. First of all, you could have said, I have no idea. Second of all, you could have said, this is the inverse. And third, you could have said, this is the derivative. Derivative, okay? How do you know which is which? The inverse would be with a minus 1. The derivative is with that small apostrophe. Okay, so here we're talking about the derivative. And so for finding the derivative of this, we can just go ahead and try it. And so here we have h of x equals 2x times e to the power of x plus 3. And so if you go ahead and do the derivative of this, we encounter something interesting. And so here, and Davey loves to do this, you have two x's interacting with each other. Technically, you have this first term here and this second term there. Okay, so it's very useful, especially for these scenarios, to think about it as two different terms. I know technically it's one term because it's being all multiplied together, but let's split it in half just to make this a little bit more friendly. Why is it important to do this? Because when you have two x's being multiplied closely together, technically you're walking into the product rule. And so the product rule in derivatives looks absolutely nasty. But really, if you take a closer look at this, okay, really here it's saying that, okay, in some function you have u times v, okay? And so if you do the derivative, basically, on the one hand, you will first leave u, whoops, let me pick a color that actually works here. So first you will take u and not touch it, and multiply it by the derivative of the other one. And then you will take v and not touch it, and multiply it by the derivative of the other one. And so now suddenly becomes a little bit more friendly. Basically, you touch one side and not the other one. Then you add and you flip it. Then you touch the other side and do the derivative of the other one. See? Now I know that was a lot of blah blah and it probably sounded hella confusing. Let's see it in action. And so on the one hand, you will first leave 2x untouched and multiply it by the derivative of e to the power of x. Now, what is the derivative of e to the power of x? E to the power of x, you can know it by heart, or you can just use the formula booklet. Remember, you guys, the formula booklet has a bunch of stuff inside of it, so might as well get to know what's in it, because the day of the test, it is an additional tool that you can use, okay? So once you study with the formula booklet for a little bit, you will remember, there's a section with derivatives, and you're going to look for it, and boom, you're going to find derivative of e to the power of x. So if you do the derivative of e to the power of x, you end up with e to the power of x. Yes, that is kind of troll, I'm not going to lie, but this is a formula booklet. You gotta trust it. You gotta believe in the process. And so right now, this 2x that I wrote down is untouched. Okay, I did not do the derivative of this first half. Okay, this is my u. I'm not touching the u. All right, but I do have to do the derivative of e of x, and I just found out that the derivative of e of x is quite simply e of x. So this first part is a little bit troll. I'm not gonna lie. See, now I need to add and doing the derivative of this one and not touching the next one. So the derivative of the first one of the 2x is just going to be 2. How do I know this? Because 2x is the derivative of, is it not here? That would be crazy. Here it is, derivative of x to the power of n. And so as you can see, when you have the derivative of x to the power of n, which is basically just some x that's alone. Whoops, all right, now it came back. All you really have to do, okay, is notice, focus on the n. So the n first goes in front and then gets a minus 1. So for example, 3x squared is going to be 3 times 2 times x to the power of 2 minus 1, which is just going to be 6x to the power of 1, which is just 6x. Okay? And so if we have 2 times x, is you have a 1 up here, right? So it's going to be, this is going to go in front, so it's going to be 2 times 1 times x to the power of 1 minus 1, which is just going to be 2 times x to the power of 0. And anything to the power of 0, ladies and gentlemen, is just going to equal 1. So this is 2 times 1. Oops, that is not a 1. Ends up as 2 times 1, which is just 2. Bada bim, bada boom. So over here, the derivative of the first one is just going to be 2, and the second one I do not touch it because of the product rule. If I go back over here, this is the one I'm not touching. See? So I'm not touching the second one that showed up, right? My v. I'm not touching e to the power of x. I just leave it as it is. And the plus 3, what happens to it is that it disappears. Okay? Whenever you have a constant, that constant is going to disappear. The hardcore mathy explanation is that technically there is an x to the power of 0 here. And so here, this 0 would multiply in front. You end up with 3 times 0 times x to the power of 0 minus 1. This whole thing is just 0. See? So that is the hardcore math explanation. But I think we should just stick to the idea that if it doesn't have an x, it disappears. Okay? So boom. There is the derivative of h of x. That is for part B. And for part C, they put a very important word. They say hence. Whenever you find hence in the IB, it's a massive hint for, what you used earlier, you have to use now. And so whatever you use from part B or part A, but most likely the one that was right before, so part B, you need to use what you had from part B in part C. This is worth mentioning because a lot of times exercises are set up like that, okay? And so it's a massive hint for what you need to do moving forward. So hence, find the coordinates of A. What the heck was A? That's what I mentioned earlier. A is the local minimum at point. A is the local minimum, which is right here. And so how in the heavens does the derivative help me find point A? Well, point A is a local minimum, right? And so why is the derivative useful? Why do people use it in the first place? Ladies and gentlemen, whenever you have, for example, you have something like f of x, see? F of x equals, I don't know, x squared, I'll make it up, see? So f of x equals x squared. So, from here, you guys, if you plug in a value for x, you get a value for y. For example, if you plug in, I don't know, 0, you get 0. If you plug in 1, you get 1. If you plug in 2, you get 4. If you plug in 3, you get 9. See? And all of these, you guys, are different sets of points. So this is without derivative. So without derivative, you get a bunch of different sets of points. With the derivative, it's a little bit different. So with the derivative, here I end up with 2x. And so with the derivative, it's not a set of points anymore. It's actually, you plug in an x, and you get a slope. Damn. So if you plug in 0, the slope is 0. If you plug in 1, the slope is 2. If you plug in 2, the slope is 4. If we plug in 3, the slope is 6. What? What is this? Guys, whenever you do the derivative, suddenly you're not getting points, you're getting something a little bit different. So for example, here, it's at 0, my slope is 0. Here it's at 1, like x equals 1, my slope is 2. So on and so forth. So this is x equals 2, slope 4, and this one is x equals 3, slope 6. And this actually makes sense because if you go ahead and look at the graph of x squared, which is which I'm going to show you in just a second. Yeah, so if you look at this function here, it makes sense because we said, okay, at x equals 1, for example, our slope we said was, where is this? At x equals 1, our slope is 2. At x equals 2, our slope is 4. And so here, it makes sense to have a slope equal to 2 because it's positive and it's growing. And that x equals 2, would you say that it's growing much faster? I would say that it is. So that's why the slope is bigger. See? And it's the same over here. If you plug in, I don't know, negative something or whatever, for example, let's do it. If you plug in x negative 1, you end up with a slope of negative 2, which makes sense because a negative 1 in my graph, and negative 1, my function is decreasing. Okay, so basically what I'm trying to tell you guys is that the derivative is super useful for finding out slopes, see? And so how can a slope help me find a minimum or maximum? Well, because if you take your quadratic, right? So if you take, or any function really, actually even here, see, I'm going to do it here. So here, if you start like writing down the slopes, for example, this slope here, I'm going to make it up, but it's probably like a slope of 3, see? This slope over here, it's a little bit less, it's probably a slope of 2. This right here, it's probably like a slope of 1. And at the minimum, what is my slope, you guys? Da, 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 da. It's a horizontal line. It's a slope of 0. So this is massive. Whenever you need to find max or min, derivative and equal to 0 gives you the x value. Because if you put the derivative equal to 0, basically you're doing the question the other way around, right? You're saying slope 0, what's x? That's what you're asking. So if the slope is 0, what is x? The minimum and maximum always has a slope of 0. And so for finding the coordinates of a, you're going to take your derivative and equal it to 0. So let me make a little bit of space because it's about to get a little bit juicy. So here we go. So if you take your derivative and equal it to 0, you end up with 0 equals 2x times e to the power of x plus 2 e to the power of x. All right, this looks kind of crazy, right? So what can I do from here? Well, technically, the e to the power of x is in both of my terms. So you can actually divide by that. See? Now, if it's hard for you to visualize it, let me show you to this way. Technically, you can factor both terms by e to the power of x. So you end up with e to the power of x times 2x plus 2. And from here, you can divide by e to the power of x, which is the same as doing it earlier, but maybe it's easier for us to notice. And so basically, you end up with 0 equals 2x plus 2. And so if you want to get x alone, you of course got to do minus 2 minus 2. You end up with 2x equals negative 2. You end up with x equals negative 1. Okay. Sorry. So I just found out that this right here is negative 1. And so my point A is negative 1 comma something, right? Negative 1 comma something, how can I find that something? I need to plug in negative 1. But careful, where do you plug it in? If you plug it into the derivative, what are you asking for, guys? If you plug it into the derivative, you're asking this derivative function, when x is negative 1, what is my slope? And right now, that's not what you're looking for. What you're looking for is the corresponding y value. See? And so for the x and y values, we said earlier you have to use the OG. See? You have to use the OG. For slopes, you use the derivative. Okay? So we go all the way back and we use the OG. So I can plug in h of negative 1 into this one here. See? So you end up with 2 times negative 1 times e to the power of negative 1 plus 3. So I can work this out a little bit. This first part is just going to be negative 2. And this e to the power of negative 1, anything to the power of negative 1, or better said, anything with a negative exponent, you're going to flip it. So it's going to go on the bottom and still to the power of 1 plus 3. And so from here, because you don't have a calculator, you can just leave it as negative 2 divided by e plus 3. Alright, and so this, believe me, is your final answer. Okay? And so the point A has an x coordinate of negative 1 and a y value of negative 2 divided by e plus 3. That is for part C. Just a quick reminder, you guys, e is an actual value. E is like 2.7 something, okay? E is an actual value, and the reason it exists is because it's a little bit like the opposite of the natural log, okay? It's an actual value, it exists, it's no different than pi, alright? It's no different than pi, E actually exists, okay? So take it as just a number, this can be your final answer. It's not like an x, it's not a variable, it's a number, see? So leaving your answer like this is completely legal. If you still don't trust me, I get it because I'm a guy on the internet, but look at the final answer here. Boom. You can leave it with in terms of e or just with e because e is indeed a number. So that is for part C. And now for part D, it gets even crazier. And so here it says show that, so it's something that is true, show that this occurs. What is this? And so here you have this double sort of apostrophe, see? And so basically it is the derivative of the derivative. Dun. That sounds kind of crazy, doesn't it? So basically, you gotta do the derivative of the derivative. So this guy that I have up here, right, I need to do the derivative once again. And so let me make a little bit of space. So basically, I need to do the derivative of this thing again. So from here to here, I do the derivative again. And I already know what's the derivative of this whole thing from part B, right? So the derivative of this whole thing is just going to be 2x times e to the power of x plus 2 times e to the power of x. See? So that is the derivative of that whole thing. Okay? It is straight from part B. It's nothing new. It's the product rule and all that stuff. See? And now I need to do the derivative of this second term over here. See? And so the derivative of that, well, we already saw that the derivative of e to the power of x is quite simply e to the power of x. So here you end up with plus 2 times e to the power of x. And so this is what you end up with, okay? Now, we're not quite done because in part D, they're asking us to leave it in this sort of form. And so to leave it in this sort of form, once we already did the derivative of the derivative, we need to organize our values a little bit, right? And so the main hint that I can notice is that, they're factorizing by e to the power of x. So I should probably do the same. So you can do this later, you can do this now. I'm just going to do it now because maybe for some of us it's easier to like comprehend it. So if you go ahead and do it now. So if you take e to the power of x out of every single term, this first one is going to be 2x. The second one is going to be plus 2. And this third one is going to be plus 2. So you end up with e to the power of x times 2x plus 4, which is exactly the same as what they have down here. So that is for part D, part I. Then we need to do part D, part double I, and it asks us to find the values of x for which the graph of h is concave up. Alright, you guys. And so this is an awfully specific thing that you pretty much just like have to learn. Okay? I don't like to put it like that, but unfortunately it's true. I'm pretty sure this is not in your formal booklet, and this has to do with the buzzword concave up. And so there's two big hints for what you need to do. On the one hand, part D has two parts to it, right? It has part I and part double I. And whenever you have part I, part double I, they are always related, okay? And so to find the part where it is concave up, you need to use the derivative of the derivative, okay? And this is the sort of thing that I'm just going to tell you, okay? For concave up, so concave up, you're going to be doing the derivative of the derivative being positive. And for concave down, it's going to be the derivative of the derivative being negative, okay? I know that the derivative of the derivative might be a little bit hard to explain, so let's try to explain it now, see? So we said that the OG gives you x and y values, see? We said that the derivative now gives you slopes, see? And so the derivative of the derivative, what it gives you is sort of like the slope of the slope, which I know sounds crazy, but it's basically the rate of change of your rate of change. So for example, over here, right, all of these are positive, see? So all of these have a positive slope, but the question is, are they growing faster or slower? Here they are growing faster, so that means your derivative of the derivative is positive. Over here, you have a negative slope, right? But technically, it starts growing positive more each time. See? And so it sort of has to do with how fast your slope is changing or in what direction your slope is changing. And so from here, okay, from here, you can go ahead and, as I said, do the concave up being positive to 0. And so you take this whole thing. I'm really running out of space here. I'm sorry, you guys, but let me make a little bit of space up here. I think it's going to be fine. Let me use a very different color just so that we're all on the same page. Right, awesome. And so from here, let me take, I don't know, maybe dark blue. See? So from here, the concave up, I said, was the derivative of the derivative being greater than 0. And so if you do that, right, so this being greater than 0, that means that this whole thing, e to the power of x times 2x plus 4, is greater than 0. See this whole thing, right? And so first things first, because you have e of x multiplying, that means you can divide here. And boom, something very similar to what we did earlier. This goes away with this. 2x plus 4 is greater than 0. Get x alone. Minus 4 to both sides. Bada bing, bada boom to get x alone. So 2x is greater than negative 4. Divided by 2. X has to be greater than, okay, has to be greater than negative 2. Okay? And so basically that would probably be like around here, if I were guessing. So around negative 2, it starts going concave up. See? The slope sort of like starts like growing more. See? That is the sort of way you can think about it. I know that the derivative of derivative is kind of trippy and it's a little bit hard to explain, but I think the biggest intuition I can share is how fast your slope is changing. Okay? Because many times you can have a function maybe that looks something like this, right? Which you say, it's always growing, it's always positive, but each time it's growing less and less. And so this is a very good example of how, yes, you have a positive slope, but your slope is each time growing less and less. And so the double derivative here would be negative, because each time it grows less and less, but the derivative is still positive because the slope is always going to be positive. So that is maybe a better example of what I mean by the derivative of derivative. It's sort of like the direction your slope is taking in terms of growth. See? So if it's growing more than before as you travel through the x-axis, then okay, it would be a derivative of the derivative being positive. So for example, this here, I'm just going to finish giving the examples because I think it's important to get it, ¿cierto? If you have something that looks like that, like an exponential function, you would say, okay, the slope is definitely positive because all along the line it keeps going positive, and also the derivative of the derivative is positive because each time it grows faster and faster. Ah, maybe that's the keyword I can give you guys. So for derivative, it's like speed of growth. So if it grows each time faster, it's going to be positive. And if it grows each time slower, it's going to be negative. All right, you guys? So that is the main idea I'm trying to like portray to you guys. And that is actually how you solve number 7. And so your answer for part D, double I, is just going to be x greater than negative 2. And your method points were doing exactly this. Concave up is taking the double derivative and making it greater than 0. Ladies and gentlemen, that is number 7, and I hope it helped.
All right, you guys, and now for number 8, we walk into what we call a arithmetic sequences problem. Well, later on we have geometric sequences, but immediately the massive buzzword that we should be thinking about is the word sequences. Okay, so let me first talk about what sequences are, and then we'll jump into this specific problem. And so a sequence has two different sort of worlds, right? So you have the arithmetic ones, as you saw earlier, and you also have the geometric ones, okay? And so arithmetic ones are for adding and subtracting, and the geometric ones are for multiplying and dividing. And so an arithmetic sequence, an example could be 2, 4, 6, 8, 10. Okay? And so here, each time, what are you doing? You're adding by 2 each time. And so for an arithmetic sequence, the main idea here for the plus 2 is that you have what we call a common difference of how much? A common difference of 2. So that means d equals 2. It's specifically d, and in the formulas that you're going to see for arithmetic, you have the d letter associated to it because of difference. Okay? For geometric, an example I can give you is, for example, 2, 4, 8, 16, 32. And so what's happening here? Well, before it was for adding or subtracting, now it's for multiplying or dividing. So here you have to be multiplying by 2. So 2 times 2 gives 4. 4 times 2 gives 8. 8 times 2 gives 16. And 16 times 2 gives 32. And so here it's not common difference anymore, but rather common ratio. And here is also a common ratio of 2 because it's multiplying by 2. So r has to equal 2. Okay? Why do I talk about R? R because of ratio, and it's relevant to know this small sort of technicality because in your formula booklet, if you go to the part of sequences, okay, it's important to be familiar with the formula booklet, you're going to find that you have 4 formulas, you guys, okay? So you have this first one, this second one, this third one, this fourth one. Now, first things first, you can immediately notice that the two that are up top, which I'm going to put in green, okay, the two that are up top are for arithmetic. And the two that are on the bottom, which are going to be in blue, are for geometric. And so it's important to first know that these tools and formulas exist. So the moment you read the word sequences, you think, okay, these tools are at my disposal. And you also need to know how these tools work, what is related to them, etc. And so as I mentioned earlier, you have common difference for D, which is why for arithmetic, you have D going around, right? While on the other hand, for geometric, which is common ratio, you have an R going around, okay? And so understanding R and D in that sense is already like useful, right? What is the other observation we can do? Well, they both, like the two up top, right, for arithmetic, you have one for nth term and you have one for sum of n terms. And on the bottom, for geometric, you also have for nth term and you also have for sum of n terms. Now, sum of n terms makes a little bit more sense. For example, S of 3 means you're adding the first term, the second term, and the third term. While on the other hand, for nth term, that means that, for example, you're trying to find U6, right? And so for finding U6, you plug in n equals 6 into this formula here. See? And so nth term is like you're finding one specific term, and sum of n terms is a little bit more straightforward. S of 3 means you're adding up the first 3. S of 7 means you're adding up the first 7. And now the last thing I'm going to mention is that you have I've been saying this whole time they have 4 different formulas, but I'm sure some of you already noticed, wait a second, don't I have more than one? And I would say, yeah, you're kind of right. Okay? What do I mean by this? Down here for geometric, okay, for the sum, right, you have 2 equal signs. Okay? And so that means that this equation on the left is the same as the equation on the right. Now, do they ask for the same things or not? For example, the one on the left asks for u1, asks for r, and asks for n. While the one on the right asks for u1, asks for r, and asks for n. And so, okay, so both of these equations are technically the same. They might be laid out differently. For example, the bottom has r minus 1, while on the other one you have 1 minus r. But technically, they're asking for the same stuff. There aren't different variables here that they're asking for, and so intrinsically, they're the same. Okay? While up here, for the sum of arithmetic, if you take a closer look, you have 2 different formulas here, right? But what do they each ask for? And so the one on the left is asking for u1, is asking for n, and is asking for d. While the one on the right is asking for also u1, also n, but not d, instead un. And so these small differences are the kind of thing that the day of the test can really add on to help you know what to do. So guys, these are your tools, and having clear what they ask for, what you need for each, is absolutely essential, okay? And I'm not saying you have to know this by heart, but you first need to have the intuition, okay, the moment you read sequences, you're thinking of, I have 4 tools, right? And of these tools, I remember there was this guy online saying something about like, some of these formulas have some things in common, other things not. You're not going to know it by heart because, spoilers, almost nobody does. But what you will know by heart is, there's a difference. What was the difference? And so you're going to do the same exercise as I did now and say, okay, so there's 2 equations here. For the one on the left, you need n, u1, and d. So you're going to write that down. And for the one on the right, you need n, u1, and only un. And so that's the main difference here. That is a big hint for which one can be more useful than the other one. And so this is more of a generic approach I'm trying to give you. You guys, in general, the procedure you should be doing is that you read buzzwords. You read, for example, arithmetic sequence, or you read, for example, sum of first, and boom, you're already thinking, okay, so the tools I be using are these over here. Now, this exercise is a little bit different because they actually give you And so, as I was saying, for the procedure of this exercise, right, you're going to be identifying the buzzwords. And so, this exercise is a little bit more of a special scenario because, you need to find this. They tell you that the sum of the first n terms of the sequence is given by this here. And so, the formula for sum that you can use isn't just these ones, okay? But it's also this additional one over here, right? And so, the one over here is a special one just for this specific arithmetic sequence, okay? So just for this specific arithmetic sequence, you can also use this sum of this formula, sorry, right? And so if you do the exercise over here that for the formula booklet, you need U1, you need N, you need D, or you need U1, you need N, and you need UN. Over here, what do you need? Look at that. You only need n. And so for part A, part I, for finding the sum of the first 5 terms, well, first 5 terms is a big hint for n equals 5. And so for the sum of the first 5 terms, you only have n equals 5. You do not have u1. You do not have d, right? And you do not have un, right? And so you only have n, and thankfully the formula they give you only asks for n. And so for part AI, it's pretty straightforward. You just need to plug in n equals 5 into the formula they gave you. Now you plug in n equals 5 everywhere just to be organized. So that means that even this little n is going to turn into 5. So s of 5 equals 5 squared plus 4 times 5 is going to equal s of 5. It's going to be, well, 5 squared is 5 times 5, so 25 plus 20. S of 5 equals 45. So for part AI, we have that the sum of the first 5 terms is going to equal 45. Now let me put this in red, okay? Just so that, actually that looks very ugly. So let's put that in blue to remember that this was my final answer for part AI. For part A double I, we have that given that S of 6 equals 60, find U6. Now, before I tackle this exercise, there's a massive sort of thing I want to teach you, okay? First things first, an exercise which has 2 parts in terms of like part I and part double I, um, they're always going to be related. And so part double I needs something from part I, okay? And more often than not in the IB, although not always, but more often than not, what you do in part B needs something from part A, okay? And so on and so forth. It's not always the case, but sometimes it is, and it can be a massive hint on how to move forward. There's a very direct way to know if it's the case, right? And it has to do with the special word given. And so usually when they say given, it can either be like given what you did earlier, right? But other times the given is just like given and something they give you, quite literally. And so here it's given that S of 6 equals 60, find U6. And so this is a big hint. It's like, from part A, part I, plus the fact that S of 6 equals 60, find U6. And so these are a bunch of hints that you identify because first, it's part I and part double I, and secondly, they gave you this with the big buzzword given. Okay, and so this is just test taking skills, and you gotta have that in mind, right? And actually, this shows up all over the place. For example, here you have hence or otherwise, so it's telling you that for part B you need to use that. And over here you have given this, and so given this, you're gonna find V5 for part E. Now, that's just be on the lookout for the word hence. Okay, the IB loves to use the word hence, and just keep it in mind. Okay. Anyways, enough blah blah. I'm pretty good at that. For part A double I, they tell you that S of 6 equals 60. You know that S of 5 is 45 from before. So what is U6? And this is actually very straightforward. And let me explain it with the following idea. And so you know that S of 6, actually, let's start with, you know that S of 5 equals 45. And you know that S of 6 equals 60, right? Now, what is S of 5? S of 5 is the sum of the first how many terms? Of the first 5 terms. So S of 5 is just the first term plus the second plus the third plus the fourth plus the fifth. while the sixth, while S of 6, sorry, is the first plus the second plus the third plus the fourth plus the fifth plus the sixth. And so from here, if you do, for example, S of 6 minus S of 5, well, visually what you end up doing is this goes away with this, and 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 this, bada bim, bada boom, boom. So S of 6 minus S of 5 gives you U6. All right, and so technically 60 minus 45 is going to equal 15. All right, and so, well, I mean, if I plug everything in, it would be that 60 minus 45 equals U6, right? And so 15 equals U6, okay? That is what I meant to say. But anyways, I think visually it's very appealing. And there it is, okay? So U6, right? So U6 has to equal 15. Let me put it in light blue just so that I remember that this is what we did for part A double I. Now for part B, we need to find U1. And so for U1, there's a couple different approaches that we can use. There's actually like a lot of different methods. And there's one really quick way and one more hardcore mathy way. And so I'm going to start with a hardcore mathy way because it has a lot to do with procedure and formulas and stuff like that. And so when you need to find U1, immediately ask yourself which formulas have U1. And so you go to your formula booklet, and which formulas have U1? Well, both of the sum ones, right? Both of the sum have U1. And U1 is also up here, right? But what's the problem? Even though one up here, what does it ask for? It asks for D. Do we have D yet? No, we don't. And so you cannot use this one, and you also cannot use this one over here, right? Because you don't have D. And so you only have one remaining option, this formula on the right side. So do you have U1? I mean, you don't have U1, but you have everything else. So let me show you how that plays out, right? So you have everything else as you're about to see. So that formula from the formula booklet is S of n equals n divided by 2 plus, no, sorry, parentheses, my bad. Happens to all of us. Parentheses, U1 plus UN. And so from here, you gotta start considering, like, what variables are here. And so technically, I did say earlier that you have three. You have U1, you have N, and you have UN, right? But technically, and this is about getting familiar with your formulas, getting creative as well, which has to do with you using them a lot. So always start with the formula booklet. Technically, the other variable is also Sn. And so if you find a way to plug in, for example, this, and this, then you only need to solve for U1. Okay, so that's the game plan that we're going for now. Is there a way where I can plug in the other three and get U1 alone? And so technically from earlier, you found that, for example, S of 6 is 60. And so S of 6 is using n equals 6. So, that means down here, I have S of 6 equals 60. That also means that n has to equal 6. And do you have U6? You have U6 because you know that U6 is equal to 15. And so suddenly, you can now plug in all the ones that I put in green. Okay, you can suddenly plug in here, here, and here, and end up with only U1, which is what they're asking for part B. And so from here, if you plug everything in, you end up with 60 equals 6 divided by 2 because of n, parentheses U1, plus U6. U6 we said it was 15. Okay? I might have gone a little bit too fast there, so let me go piece by piece. If you first plug in n equals 6, you end up with S of 6 equals 6 divided by 2, parentheses U1 plus U sub 6, right? And so what is S of 6? We said that S of 6 was 60 equals 6 divided by 2 is 3, parentheses U1 plus U6, which is 15. And so from here, because it's all being multiplied, the 3 in the parentheses, you can divide by 3 to both sides. You end up with 20 equals u1 plus 15 minus 15 minus 15. Bada bim, bada boom. U1 equals 5. Okay? So this is the hardcore math way to solve it. You just use the formulas. Always consider the option of plugging in for S of n. I know it's kind of weird because you don't usually you're trying to find S of n, right? And so you as long as you practice with these formulas and look at different examples, you keep getting into the creative options, and that way the IB won't catch you. See? And so that is one creative way to use this formula. I know earlier I said you need U1 and an UN to use this formula, right? These three things. But technically, right, if you have S of n as well, you can start like you can have 3 out of 4 and find the last one. So that's what I'm trying to tell you, okay? Which is what we did over here. Anyways, so that is one way to do part B with the hardcore mathy way. So U1, as we said, has to equal 5. Let me box it in and put it in blue so that we remember that this is my final answer. Now, that being said, there is another way to find U1, which is fairly quick, and I would like to show it to you guys, okay? And so technically, if I look at this example for the arithmetic sequence over here, right? So technically, think about it this way. And this is a very logical approach. And so S of 3, for example, is going to be the sum of the first 3, right? S of 2, for example, is going to be the sum of the first 2. And S of 1, I know it sounds kind of troll, but technically S of 1 is just the sum of the first 1. And so what I'm trying to tell you is that S of 1, it's just the sum of the first one. So S of 1 equals U1, and from here, well, you have this sum formula over there that asks only for n, so you can plug in n equals 1 here. You end up with S of 1 equals 1 squared plus 4 times 1, right? And so S of 1 equals 1 plus 4. S of 1 equals 5. And you know that S of 1 equals U1 by logic, right? And so here you can say that, because S of 1 equals 5, then U1 also equals 5. This is another way to do part B, okay? I'm just giving you all the tools you need. Might as well, show you all the options. Why not, right? Anyways, that is for part B, all right? Technically, you can also plug it in over here. So I'm just going to show you that quickly. Even here, if you plug in n equals 1, you end up with S of 1 equals n divided by 2, parentheses U1 plus U1. Oh, that's interesting. Oh, and n is 1, right? And so S of 1 is going to equal 1 half, parentheses 2 U1. This goes away with this. This is literally proof that S of 1 equals U1, okay? So trust me, you usually shouldn't trust guys on the internet, but just for today, trust me, S of 1 equals U1, okay? Yeah, and then for part C, they use the buzzword, hence or otherwise, write an expression for, and this is interesting, UN in terms of n. And so this right here is very important for us to understand, first of all, what it's actually asking for. And so what it's actually asking for here, when it says UN in terms of n, is basically that UN is alone. Okay, so careful with that. UN is alone, and you have a bunch of different n's on the other side. You might have a plus or 3, you might have a plus 3 somewhere, a plus 2, but you only have a bunch of n's on the right side, okay? And so keep that in mind. UN in terms of n means you have UN alone equaling a bunch of different n's doing a bunch of different stuff. And so it's our job to figure out how that plays out. Now, I think from here there's two different approaches, and part C is kind of hard. Okay, so I'm going to immediately say that part C is kind of hard. So there's definitely a challenge coming up, right? So on the one hand, specifically to this exercise, you have that S of n, right? That one of the formulas for sum has only n's inside of it. And so this might be useful for leaving it in just in terms of n. But you might be thinking, yo, what about un? Don't you need un? Un isn't in here. And so that is when you start thinking, okay, where do you have un? Un, you have it. Actually, once again, un, you have it only in two places, right? Un is only in what I'm putting now in pink. So un is over here, and un is also over here, right? So there's un, and here's un. And so these are two different approaches, right? So the one up top, well, for using this one for getting un, just in terms of n, you need to find d. So if you find d, you're good to go. And for this one on the bottom right, well, basically, the problem is they have s of n here, right? And so, here's something interesting. That equation from the formula booklet is that s of n equals n divided by 2, parentheses, u1 plus un, right? And so you pretty much have all of this because you already have u1, right? And un is the expression you're trying to leave it in. But the problem is s of n. That is what's annoying you. But what is s of n? S of n is also this whole thing. So wow, this is kind of whack, but technically you can say s of n equals s of n, and I know that looks troll, but basically you're plugging in this guy in orange here and this guy in pink over here. And so if you go ahead and do that, you end up with n squared plus 4n equals n divided by 2, parentheses u1, we know that u1 is 5, plus un. And so yes, this looks super nasty, but wait a second. Technically, you only have two variables. Technically, you only have n and un. And so, that makes it a little bit more friendly. So if you get un alone, you end up with un in terms of n. So that being said, to solve from here, you want to get un alone. I think it's easiest if you first multiply everything by 2 to get rid of this fraction. So you end up with 2n squared plus 8n equals n, parentheses 5 plus un. You want to keep getting un alone so you can divide by n, like everything, right? And so, well, technically here, just to be more accurate, would be all of this divided by n. And so this goes away with this. You end up with 2n plus 8 equals 5 plus un. So you can do minus 5. Minus 5, you end up with un equals 2n plus 3. That is a way in which you can do part C. Now, part C is pretty hard to spot, and so let me go over the procedure just one more time. So because you need the expression for un in terms of n, you first thought, where the heck do I even have the symbol un? And you have it in two places. You have it in the equation up here and the equation down there. And so which one is more useful? Well, the one up top, you first need to find d, and with what we've done, we still don't have d. And for the one on the bottom right, well, you have s of n. S of n is annoying. But can you replace s of n with something? You can replace it with this, which is only in terms of n. Alright? So that was the logical approach that we employed. And technically, if you find d, then using the equation up top is like doable, right? And so I'm going to show you real quick how you can find d. Now, d is the common difference, right? And you can always find d, and this is important, you guys. You can always find d as long as you have two different terms. And so because you have u1 and u6, you can find d. As long as you have two terms, you can find d. All right, so that being said, you know that, I'm just kind of running out of space here, but you know that u1 is 5, and you know that u6 is 15. And so to reach from u1 to u6, how many times do you apply d? Well, I think it's good to make this like super visual, right? And so if I add a lot of visuals to this, you can put the term u2, u3, u4, and u5. And so technically, yes, you don't know what U2, U3, U4, and U5 are, but you do know that to go from U1 to U6, how many times did you apply D? And so the same idea I did up here of doing plus 2, plus 2, plus 2, plus 2, you can think about it down here as from here to here you did plus D once to reach this guy, right? And then plus D again, 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 right? So how many plus D's was it? It was 1, 2, 3, 4, 5. So that's telling me that U1 plus 5D has to equal U6. Pretty logical, right? And so if you plug in the values, you have that 5 for U1 plus 5D has to equal U6, which is 15. So get D alone, right? Minus 5 to both sides. So 5D equals 10. Divide by 5, divide by 5. D equals 2. And so now that you know that D equals 2, oh, you can plug it in over here, right? And so UN has to equal U1, which we know is 5, plus N minus 1 times 2. We know that D is 2, right? Now, I know that this 2 looks a little bit troll in the parentheses being at the end, but guys, it's no different than if it was in the front. Okay, so I'm going to leave it in the front just because it's a little bit more friendly. Blah, 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 blah. But from here, if you distribute, right, you end up with UN equals 5 plus 2n minus 2. You end up with UN equals, oh, look at that, 2n plus 3. Sounds familiar? It better be. It's the same thing that we got over here. UN equals 2n plus 3. UN equals 2n plus 3. So again, two different ways to approach it. You either identify that, oops, I need to find D, or oops, I need to solve the fact that S of n is annoying me, right? So you either plug in something for S of n, or you discover what D is using the different terms. So yes, keep it in mind, you guys. Whenever you have two different terms, you can always find D, and it's the same for the common ratio, okay? Which is actually what's coming now. And so later on, they tell us that considering a geometric sequence Vn, where V2 equals U1 and V4 equals U6. All right, interesting. We need to find the possible values of the common ratio R. And so what they're telling you here is a little bit weird, okay? And so first things first, here they're associating, right? I mean, we gotta leave something clear. So for geometric and arithmetic, they always think in terms of U, okay? So like UN is on both, U1, U1, like they both arithmetic and geometric, like they use the letter U for the terms. But over here, they plug in or they give you Vn, okay? And so this is just to sort of like tell you that, okay, when we're talking about the geometric sequence, it will be with V. When we're talking about the arithmetic, it will be with U. And so they tell you that V2, so the second term of the geometric, is equal to the first of the arithmetic. And that the fourth of the geometric is equal to the sixth of the arithmetic. And so if I, before even answering part D, I just highlight that information more visually. So you have that, well, you have some first term, right? Then you have your second, your third, and your fourth for the geometric, right? And you know V2 and V4. And so V2 is equal to the first of the arithmetic. And the first of the arithmetic was, it was 5. V3 you have no idea, but V4 they tell you is the sixth term of the arithmetic, and the sixth term of the arithmetic is 15. And so guys, to reach from 5 to 15 in the geometric, how many times did you apply R? So you applied it once here, and you applied it once over here, right? Now, clearly you ended up with a bigger number, so you know it's multiplying, see? Now, technically, it's always multiplying because if it's less than 1, it gets smaller, but just for us to think about it, we're going to think about it, it's multiplying, not dividing, okay? Whatever, it's growing, it's got to be multiplying by something greater than 1, okay? So, the common ratio you apply r twice to reach 15. So 5 times 2r has to equal 15. And so careful, here's a slight difference. It's not going to be 5 plus 2r. We're now in the world of geometric. It's 5 times 2r. And so technically you end up with 10r equals 15. And so from here, because you want to get r alone, what you can do is divide by 10 to both sides. So r has to equal 15 divided by 10. Now, I made a massive mistake here, and I'm going to leave it on the video because we all make mistakes, and that's just fine. See? My massive mistake is that, yes, r is being applied twice, but it's being applied twice by multiplying. It's not being applied twice by adding, which is by putting 2r. It's being applied twice by multiplying. So technically here, instead of 5 times 2r, it should have been 5 times r squared. So I'm sorry, you guys. I trolled you a little bit, but hey, we all make mistakes. I'd rather leave it on the video. And it's a common mistake, so I think it's also a good idea that you leave it on the video. See? Anyways, point is when you're applying the common ratio, think about it as squared, cubed, etc. because it is multiplying, right? So whenever you have, I don't know, x times x times x, you're gonna add the exponents, right? So you end up with x cubed. Whenever you have x plus x, you end up with 3x. You're adding the constants that are in front, okay? So it's a slight difference, and I messed it up. Happens to anyone. Let's proceed, okay? So now I'm putting it as I should have. 5 times r squared equals 15. And so from here, you want to get r alone, so you can divide by 5. Divide by 5, r squared equals 3. Whoops, sorry about that. And so from here, you can, you want to get r alone, so you do square roots to both sides. In order to get rid of the squared, you end up with r equals 3. Now, careful. Because you're square rooting, your answer is going to be r equals plus or minus 3, which actually makes a lot of sense because for part D, they're asking for the possible values of the common ratio r. Also, the possible values is either r being positive or r being negative. If you've never understood well why square root of something gives you plus or negative, let me explain. And so technically, if you're looking for the answer of, I don't know, square root of 4, right? Immediately you're going to tell me, it's 2. Now let's understand for a second why it's 2. It's 2 because 2 times 2 gives you what's inside the parentheses, gives you 4. And so technically, when you write this, you're asking, like in math terms, what number times itself gives me 4. And so 2 times itself gives you 4. So 2 times 2 gives 4. But you guys, negative 2 times negative 2, how much is it? It's also 4. And so that's why for this square root, if it's base 2, right? I mean, I think it's called base, but whatever. Whenever it's like a normal square root, right? You can do this association, right? So you can do this association where it's either positive 2 or negative 2 because of these two different scenarios, okay? So anyways, for part D, that is why r has to equal plus or minus 3. And so now for E, they tell you that given that v of 99 is negative, find v5. All right, and so this is a little bit of a curveball, you guys. Okay, and so here is something we need to understand. So for all these different sort of values, okay, for your geometric, r can be positive or negative. Now, you haven't discovered yet if r is negative or positive, right? And so this information here is a big hint to see if r is going to be positive or negative, right? And so think about it this way. If you were always multiplying by like a by positive 3, would you ever end up with a negative value in your geometric sequence? Technically, no, right? And so if you're multiplying by a positive value and your terms are already positive, they're never going to go negative, okay? But if you're multiplying by a negative value, some of them will be positive and some of them will be negative. Why do I mean some of them? Because, for example, over here, I don't know, let me make something up, see? So let's say you have a geometric sequence of r equals -2, right? And so if you're multiplying by -2, you can have, I don't know, you can start with +2, then it goes to -4, then you have +8, then you have -16. And so, yes, it's increasing, but some of these values are positive, some of these are negative. Now, if you start with a positive, like, first term and r is positive, then your values will always stay positive, right? The only scenario that can be like a little bit tricky, right, is if your first term starts negative. So if your first term starts negative, but your r is positive, then everything will stay negative, okay? And so think about it this way. The only scenario that should really, really catch your attention is if you have alternating symbols. So if you have alternating symbols, that means your r has to be negative. Okay, that is the only hint I can sort of like give you. Okay, so if they're alternating, your r has to be negative. And so here, they're telling you that your 99th term, which is way out, right? So your 99th term is negative. Your 99th term is less than 0. And so if somewhere along my line of math, I have some that are positive and some that are negative, r by logic has to be negative. The other way you can think about it is that, for example, in this example, right, the ones that were odd, so v1, this is v2, this is v3, this is v4. So in this example, the ones that were odd are positive, while the ones that are even are negative. And over here, what you can actually end up with is that the even ones are positive, and here the odd one for 99th term, 99 is odd, so the odd ones are going to be negative, right? V5 is negative, that means R has to be negative. So I said the same thing in a lot of different ways. I'm sure one of them worked out for you. See? So anyways, for finding V5, all you really have to do is take this 15 from before, the V4. So you take this 15, you multiply by R, and that gives you V5. So just to be a little bit more organized, actually, V4, right? So V4 times R will give you V5. Okay? So V4 times R gives you V5. V4 is 15. R we just identified has to be -3. And so that will be my V5, right? And so 15, right? 15 times -3 has to equal V5. And so from here, actually I missed something small over here. So this is plus or minus square root of 3, you guys. Okay? And so technically from here, my bad on that, right? So you do square root of both sides, you end up plus minus square root of 3. Apologies. This is from way earlier, right? You end up with 15 times -3 equals V5. And so V5 has to equal basically -15 square root of 3. All right? And so apologies for that. On this step over here, everything was going just fine, but I needed to leave it as plus or minus square root of 3. So small detail there. I'm sorry, you guys. But now I recognized it, so there it is. For part E, V5 has to equal -15 square roots of 3. That is how you solve number 8, and I hope it helped. Alright, you guys, and now for number 9. It is pretty hard, it is pretty annoying, there is a nasty function, and there's an even nastier graph. But the good thing about this nasty exercise is that it tends to show up. And so however hard it may be, you can prepare for it with a pretty good amount of certainty. So, at least in my experience, from what I've seen, there's quite a few exercises that talk about displacement, that talk about acceleration, that talk about velocity, all in one exercise. And so seeing how they are related to each other, how to go from one to the other, what it means by speed, distance, displacement, the differences between all of that, it is very, very relevant to be familiar with it so that you can get all of these points, which, by the way, are quite a few for just one exercise. So, that being said, for number 9, the context it gives us is that we have an object. It moves along a straight line at its velocity in meters per second. Okay, so its velocity v, meters per second, at time t seconds, is given by this function here. And they tell you that this is for values of t that go from 0 to 4. Now, pop quiz. What is this? This, ladies and gentlemen, is what we will call our domain. What is the difference between domain and range? Intuitively, domain is like your possible x values, while your range, you guessed it, is your possible y values. And so my possible x values can only go from 0 to 4. Why do I know it's x values? Because this t that's shown here is in your x, it's in your horizontal. See? That's what I'm trying to say. And your y is going to be velocity. Okay, awesome. And so if it goes from 0 to 4, you know for a fact that over here you have a 0, and over here you have a 4. And so, again, this is just context, understanding like what's going on, okay? They tell us that the object first comes to rest at t equals k, and that the graph of v is shown in the following diagram. Now, because this is an object, moving along a straight line, correct? Then that means that when velocity equals 0, you guys, is when the object comes at a rest. So when it comes at a rest, it means that it's not moving. And so when is it not going to be moving? It's not moving if velocity equals 0. Now, velocity equaling 0 means that my, it means that I am on my x-axis, right? Okay, that was not a good line. If velocity equals 0, that means you have a y of equals 0, and it means you have to be in your x-axis. And so not moving velocity equals 0 is right here. So, that's also something that's interesting. Your value of k is actually right there. So again, this is just understanding what they're giving at us at etc. See? So the graph of v is shown in the following diagram, and at t equals 0, the object is at the origin. It's where it starts, right? So it starts off with like a little bit of speed, right? So that's interesting. Maybe it's, I don't know, already falling or something. Who knows, right? Anyways, for part A, we need to find the displacement of the object from the origin at t equals 1. And so here's something interesting. We're talking about displacement. There are two main concepts you have to get familiar with right away. One thing, oh, this is actually for later, so whoops, spoilers. So one thing is what we call distance, okay? And the other thing is what we call displacement. Now, for all our intents and purposes, all you really have to know is that whether they ask for displacement or distance in your formula booklet, you have to keep that in mind because there's a formula for distance and there's a formula for displacement. So that's a quick rundown of like, okay, identify the buzzword, use the correct formula. So there's one for displacement, one for distance. They're a little bit different. See? Notice how the one for distance has these vertical lines, which is what we call absolute value. Okay? And so that is the only difference between the two. Distance is the same formula as displacement, but with absolute values. All right. An absolute value, all that it does, for example, absolute value of -3 gives you 3. An absolute value of -7 gives you 7. Okay. Absolute value of, I don't know, 4 stays as 4. So what's happening? It turns whatever's inside into a positive value. Okay, that's all it really does. All right, now that is like, in a more practical sense, what you need to know. So there's two formulas, identify the word, blah, blah, blah. Now over here, I'd like to explain that the difference between distance and displacement is the following. So imagine you start at point A, all right? You go to point B, okay? And you end up at point C, all right? And I'm just gonna make a bunch of different numbers up. So from A to B, it was, I don't know, 4 kilometers. From B to C, it was 2 kilometers. And that's that, right? And if I were to draw a line over here, or actually, before I talk about that, so from A to B was 4 kilometers. From B to C was 2 kilometers. And so distance traveled, right, is going to be 4 plus 2 gives you 6. All right, that's pretty straightforward. It makes sense. Now over here for displacement, I'm going to take the same exercise. So you have A going up to B and then going down to C, right? Now from A to B, it's still going to be the same 4 kilometers. From B to C is going to be the same 2 kilometers, but the displacement is a little bit different. And so from A to C, the distance here from A to C is going to be 5 kilometers. And so the displacement, you can think about it as like your effective distance, okay? And so your effective distance, what really matters is like start point to end point, all right? And so start point to end point, which is just going to be A to C, was 5 kilometers. So here displacement was 5, while distance does not care about distance from A to C. It only cares about the distance you actually covered. Okay, so that's the difference between distance and displacement. Displacement only cares about starting point and end point, while distance only cares about what you actually traveled step by step. All right, enough blah blah. Let's get into the exercise more into the thick of it. For part A, we need to find the displacement of the object from the origin at t equals 1. And so you identify the word displacement, you open up your formula booklet, and there is the formula you need to use. So let's understand it more thoroughly. So displacement is going to be the integral of t1 and t2 in respects to velocity and dt. Now that's a lot of not very intuitive math terms, okay? And I also didn't use like the fancy definitions, but that's because you don't need the fancy definitions. Who cares about the fancy definitions? What's really going on here, you guys, is that T1 is going to be like your starting point, okay? And T2 in this context is going to be your end point, all right? And all you need to do is plug in your velocity function and do the integral in respect to time, right? That's what's really happening. And so if I go ahead and sort of follow this formula, well, first let me write it down. So the formula was you go from T1 to T2, and we're taking our velocity formula, right, or function, and doing it in respects to dt, all right? So if I go ahead and plug this in, think about it. They want the displacement of the object from the origin at t equals 1. So if it's from the origin, that means that t1 is going to be 0 from the origin, while t equals 1 is literally just, okay, we're going to be finishing at t equals 1. Okay, so that's what it's telling you, and if you plug it in over here, you end up with integral of 0 up until 1, so it's from the origin until you reach 1 second, of vt. Now, vt we know is negative t cubed plus 7 over 2 t squared plus 2t, if I recall, minus 2t, sorry, plus 6. minus 2t plus 6, and all of this is the integral in respect to dt. And so now I have it more set up. Now it makes a little bit more sense. And so from here, well, how do you integrate this? Lo and behold, there's a lot of different stuff in your formula booklet, and even integrals include that. And so if you scroll up, you're eventually going to find the integral of x to the power of n, and surprise, it's the only integral you actually have to know. And yes, this looks nasty over here, but let me explain it just for a second, okay? So, keep the following in mind. Basically, really focus on what is happening to n. And so this n, on the one hand, is going to get added a plus 1 on top, and the exponent, whoops, and the exponent, which I want to put in a circle now, and so the exponent, right, will also go on the bottom. Oh, interesting. So if you have x squared, for example, and you do the integral of this, you are going to end up with, well, the x squared plus 1 divided by 2 plus 1. And you cannot forget this plus c. Now, what is plus c? Plus c is going to be a constant. All right, and why is a constant relevant? Well, let me explain it this way. So, much how in math you have plus being the opposite or the inverse, right, of negative, you have multiplication being the opposite of dividing, right? And you also have that, like, the derivative, basically. So I'm just going to write it. So derivative, its partner, right, its mirror, is going to be the integral. That means if you have, I don't know, x squared, and you do the derivative of this, you end up with 2x. But if you have 2x, and you do the integral of this, right, you're going to end up with x squared. Now, here's the interesting thing. Imagine I'm doing the same exercise, just that instead of x squared, you have x squared plus 420. So if you do the derivative of x squared plus 420, you end up with 2x. Whenever you do the derivative, the constant, boom, disappears. And so if you go from the integral of 2x and you do it, right, and you end up with x squared, well, lo and behold, where is my 420? It's always 420 somewhere, guys, by the way, just saying. So, where's my 420? And so that is why you need to put plus c, because technically there's a constant that you could have eliminated earlier through the derivative. Okay, that is why you put plus c. There could have been a constant that got eliminated from the derivative. That's the friendliest example I can give. Okay, so that is why there's a plus c. And last but not least, n cannot equal -1, because on the denominator you can't have it equal to 0. So whatever is on the bottom can't equal 0. So from here, n plus 1 cannot equal 0. It's the same as saying, by getting n alone, that n cannot equal -1. So nothing too new there. You can't divide by 0. Anyways, that's just so that we understand how the integral actually works. But you can just follow like this formula step by step and it'll work out. See? So that being said, you gotta do the integral of this whole thing. And don't get nervous. Plugging in the 1 and the 0, I'll show it in a second. Okay? But for now, leave it there. Don't touch it. And just do the integral like of the whole thing inside. Right? And so the integral of the whole thing inside, if you follow step by step, so on the one hand, right, well, there's negative t to the power of 3, you still have a negative that's just going to be sitting there. And then you're going to have t to the power of 3 plus 1. And on the bottom, you're going to have 3 plus 1. For this next term, you're going to end up with plus, well, the 7 over 2 is going to stay, so we're just going to leave it there for now, right? Times t to the power of 2 plus 1 divided by 2 plus 1. All right, interesting. Let me put this in parentheses because some of these fractions will end up interacting with each other, okay? For the next term, we end up with minus 2 times t to the power of 1 plus 1. 1 plus 1 because technically there is a 1 right here that's hidden, right? So t to the power of 1 plus 1 divided by 1 plus 1. And this last term, this 6, ends up being plus 6 times t to the power of 1 divided by 1. And this last one's a little bit weird, so let me explain. Technically, you guys, this last term, much how the one previous to it had a to the power of 1, this last one has a t to the power of 0. So t to the power of 0 equals 1, so it's legal to leave it that way. And you can think about it like, also this is basically just 6 times 1, which is still 6, right? And so thinking about it in terms of t to the power of 0 helps you do this last step because, so basically what you're doing here, you're doing t to the power of 0 plus 1. And on the bottom, you're also doing 0 plus 1. All right? And so that is a way that you can sort of think about it. I think it's the best approach. I think it's the friendliest. Yada yada. Anyways, so that is just following this formula like to the heart, right? And so again, I still don't plug in 0 and 1. I'll get to that in a second. Don't stress out. But this is the heart of the integral. This is the hardest part, okay? And so once we did that, let's leave everything inside a little bit more pretty, right? Let's leave it a little bit more pretty. And so this first term, you can end up with negative t to the power of 4 divided by 4. This next one is going to end up being plus 7t cubed, right, divided by 2 times 3. And so 2 times 3 gives me 6. For this next term, I end up with minus 2 times, da, da, da. So minus 2 times t squared divided by 2. All right, so that's interesting. Plus 6t, quite literally, right? And so this third term here, you might have noticed, it has a 2 on the top, it has a 2 on the bottom, so you can go wablam, wablam, you end up with negative t squared, okay? Alright, you guys, and as I said, it's very important, I should have put it somewhere here, my bad, that you have a constant once you do the integral. So there should have been a plus c going around somewhere, right? Now you can apply sort of like the idea of the 0 and the 1. And what this is just going to do, okay, and it's always like this, is that you're going to have on the one side, on the left, you're first going to apply the bigger value. So for the 1, you're going to apply that. So you're going to apply t equals 1 first, right? So you end up with negative 1 to the power of 4 divided by 4 plus 7 to the power of 1 to the power of 3. 7 times 1 to the power of 3 divided by 6 minus 1 squared plus 6 times 1 plus c. And all of this is going to be minus, notice, it's going to be minus the side that is with t equals 0. But with t equals 0, it's a little bit troll because, if you plug in 0 here, that's going to disappear. If you plug in 0 here, that's going to disappear. If you plug in 0 here, that's going to disappear. If you plug in 0 here, that's going to disappear. But what is left? Plus c. And so this thing on the left, I'm just going to write it out so that we're on the same page, but it's really just 0 to the power of 4 divided by 4 plus 7 times 0 cubed divided by 6 minus 0 squared plus 6 times 0 plus c. And so really, if we work this out a little bit more, well, all of these will turn into 0 except for c. But you have a minus c. And so on the right side, you have minus c. All right. And on the left side, we end up with, well, this negative 1 to the power of 4 is just going to end up being negative 1 over 4 plus 7 over 6 minus 1 plus 6 plus c. And so plus c minus c, these go away. And now you end up with a bunch of fractions that you need to, well, see how they add up together and stuff and blah, blah, blah. And so from here, it's very annoying to work with fractions, but go piece by piece. And so I can put it as 7 over 6 plus 5 because of this, right? Minus 1 over 4, right? And so there's a lot of different ways to approach this. What I would suggest is first handling the the 5, okay? And so handling the 5, I can combine it with the 7 over 6. And to do that, you need to amplify. And so when you add fractions, you need the same denominator. So you need the same number in the bottom. And so for this 5, what you can do is that you can do 5 times 6 over 6. And why is this legal? Well, 5 over 5, how much does it equal? It equals 1. 4 over 4, how much does it equal? It equals 1. 3 over 3, how much does it equal? It equals 1. And so it's legal to multiply by any of these because you're just multiplying by 1. And multiplying by 1 doesn't change your number, right? That is what we call amplification. So I'm amplifying the 5 over 1 by 6 by multiplying by 6 over 6, which is the same as multiplying by 1, right? I'm not actually changing the number. It just makes it more friendly for the fractions to work with each other. And so in this step, you end up with 7 over 6 plus 5 times 6 is 30 divided by 6. So all this really was a way for these fractions to interact better. And so from here, you end up with 37 over 6 minus 1 over 4. And we're almost done. This is a little bit of an annoying part because now you need to find a way to make the denominators of 6 and 4 similar to each other, right? And so from here, what I would suggest is that you count the different multiples that each of them have and work from there. So for example, 6 has 6 times 1 is 6, 6 times 2 is 12, 6 times 3 is 18, 6 times 4 is 24. That's probably good enough. 4 times 1 is 4, 4 times 2 is 8, 4 times 3 is 12. Already found a matching pair, and so I'm going to aim to amplify both so that the denominator equals 12. For the first one, for the 37 over 6, I need to amplify it by how much? By 2 over 2, because 6 times 2 is going to give me the 12. For the other one, for the minus 1 over 4, I need to amplify it by 3 over 3. And so 4 times 3 gives me the 12. Guys, just to be very clear, this is legal because 2 over 2 is equal to 1. So you're multiplying by 1. And 3 over 3 is also legal because it equals to 1. And so I just want to insist, all of this is legal because you're just multiplying by 1, okay? So the number on the left is 37 times 2, which is, with quick maths, you end up with 74 divided by 12 minus 3 divided by 12. And so from here, you end up with 71 over 12. And what are my units, you guys? My units are meters, right? And so your displacement for part A took a little bit to do, took a little bit of explaining, but I think we ended up with a very clear answer. For part A, it has to be the displacement 71 over 12 meters. I'm going to put it in blue just so that we remember that this was my final answer. So again, a lot of steps, but hey, it's worth 5 points, worth looking into it. So that is for part A. For part B, we need to find an expression for the acceleration of the object. And so now the big buzzword is acceleration. Now what do you have? You have velocity. So how can you reach acceleration from velocity? Now I'm sure that there's at least one of you saying, dude, I'm not a physics guy, like, don't ask me that, right? And some of the physics guys out there are already saying, dude, I know how to do that. And if you're an average Joe like me and you're not sure, what you are sure about is that the IB wants you to use the formula booklet. A lot of these exercises and a lot of people would do so much better if they just understood that the formula booklet has almost everything you need for the test. It is a massive hint for which formulas to use, for which procedure is the best to use for your approach, and etc. But it's only useful if you know what's in it. And so the moment you read acceleration, you should be thinking, I know that's somewhere in here. I know I've seen it. I'm not sure where. I'll find it. And once you do, bada bim, bada boom, there it is. And so acceleration, as you can see, on the one hand, is going to be the derivative of velocity in respects to time. And the one right next to it, if I recall correctly, is the derivative of speed twice in respect to time twice. But the one we're interested in this case is just the first circle I put. And so basically, if you take velocity and do the derivative, you get acceleration. So just to be very clear, you have velocity. If you do the derivative, you're going to end up with acceleration. And I'm just saying, if you ever face an exercise that they give you acceleration and you need to reach velocity, well, you can reach velocity from acceleration by doing the integral, okay? So I'm just saying, I'm giving you knowledge because it might help out in the future, okay? What we're interested in for this step now is doing the derivative of velocity to reach acceleration. So for part B, what you can do is, well, I've explained a lot of things here. So for part B, what you can do is take your function, which we wrote down, well, it's the same one as this one here, right? And so it's negative t cubed. So velocity, right? Let me just write it again, see? So for part B, we have velocity equals negative t cubed, da da da, which is the same one up here, guys. Okay, so negative t cubed plus 7 over 2t squared plus 7 over 2t squared minus 2t plus 6, if I recall, is going to be my formula or function for velocity. All right, so this is the OG function for velocity. According to formula booklet, if I do the derivative of this in respect to time, I reach acceleration. So the derivative of this guy, which is going to give me acceleration, is just going to be the derivative of a bunch of exponents, right? And so the derivative of this, right, as you can see, you have a bunch of t's with exponents in them. And so the derivative you have to use, there's a lot of different ones you might have to use, right? For example, the tools they give you for derivative are of ln x, of the exponential, of cosine, of sine, but in this case, you're only interested in the one that's up here. And so the derivative of an exponent, really just focus on the n. Okay, so the n on the one hand is going to go in front, multiplying, and we'll also get a negative 1 to its exponent. So for example, I don't know, x to the power of 4 is going to be, well, on the one hand, the 4 is going to go in front, and also you're going to have a 4 minus 1 up top. You end up with 4x to the power of 3. This gets juicy whenever you have fractions, but I'd rather just show you an action. Okay, so that was a quick example for derivative of an exponent. If I go over here for this first term, right, so this first term, technically there's a negative 1 here, okay? And so you end up with negative 1 times 3, because the exponent went down in front, times t to the power of 3 minus 1, because you need to do a minus 1 to your exponent. For this next one, you end up with plus 7 over 2 times 2 times t to the power of 2 minus 1, because you do negative 1 to the exponent. And this next one, the minus 2t, ends up with minus 2, because technically you had a 1 here and multiplied in front, and you ended up with t to the power of 1 minus 1, which is just going to be t to the power of 0. Just to be very complete in my approach, I'm going to put it here, okay? But technically the t is just going to disappear. And for this last one, as I said, technically there is a t to the power of 0, so that means that you end up with 6 times 0 times t to the power of 0 minus 1, right? And so this whole thing ends up being just 0 because there's a 0 multiplying it, right? That being said, my final sort of form for the acceleration, because I know I'm being very thorough with these steps, but just simplifying everything a little bit. This first one, you end up with negative 3, so negative 3t. The exponent is 2. This next one, the 2's go away with each other because of fractions. You end up with plus 7t to the power of 1, so you leave it like that. And this third one is minus 2 times t to the power of 0. Anything to the power of 0 is 1, so it's just minus 2. And this last term, already said, turns into 0, so you just leave it like that. This is your formula for acceleration. And so that is for part B. Let me write it over here in case we end up needing it. A of t is going to be, if I recall, negative 3t squared plus 7t minus 2. Okay? I'd like to make one quick observation, you guys. So, a lot of times what you need from part B was necessary. I mean, yeah, what you need in part B uh, is something you did in part A, right? But not always. This is an excellent example that maybe you have no idea how to do displacement. Maybe you opened the formula booklet, you saw the integral, and you said, "Nah, I can't do that." But hey, part B has nothing to do with part A, and it's just a derivative. And always claw for points wherever you can, right? So if the day of the test you're low on time and like you reach number 9 but you have 5 minutes left and you're like, dude, there's no way I'm doing part A, but you realize part B is just a derivative, do only part B. That's fine. You're gonna get 2 points and might as well get 2 points than 0, right? So again, just test taking skills. Be on the lookout for this kind of stuff. Here's an example where part B has nothing to do with part A. So you can just do part B and get 2 points and, better than nothing. Anyways, then for part C, they say hence. This is a massive hint. Whenever they say hence, without any more context, it's whatever you did from before, you need it for now. And so part C is an example that you need something from part B. You need something from part A. We're about to figure out what. So for part C, it says, find the greatest speed reached by the object before it comes to rest. Find the greatest speed reached by the object before it comes to rest. So think about it this way, right? I mean, mathematically, for part C, all I really need to tell you is that you take the derivative of velocity and you equal it to 0. All right, this is something you can memorize and you'll be good to go, but I'd rather explain it a little bit more intuitively. Imagine you're driving like a really fast car, see? And you're trying to see how fast it goes. And so you press on the pedal to the metal, and you go really fast, right? And I don't know, you reach, I'll make it up, like 180 kilometers per hour, like a crazy amount, right? And the moment you reach that, you stay there for like 5 seconds, and then you start decelerating because you're saying, damn, I'm going way too fast. See? The point is, when you were 5 seconds driving at 180, you weren't increasing your speed anymore, and you weren't decreasing it either. And so your acceleration at the greatest speed, you you held it there for a second. See? You held it there for a second, which is the whole point. So whenever you reach the maximum speed, acceleration is going to be 0. See? It's not so different than, like, I don't know, you're throwing like a ball. See? So you throw a ball that goes like this, like a parabola, and then it lands. See? And so as the ball is flying through the air, when it reaches its maximum like height, right? When it reaches the maximum height, it's not accelerating anymore because it's not going higher up. It's actually a speed of 0. It's frozen in the air for just a second, and then the speed goes negative. See? The same idea applies here. That is why velocity, you take its derivative and equal it to 0. Whenever you find, and this is the other great idea. So if you do derivative equals 0, you're looking for slope equals 0. See? And if you're looking for slope equals 0, you're looking for an optimization, a max or a min. Whenever your slope is 0, you are looking at a max or a minimum. So if you have a function that goes like this, actually no, let me make a better example. So example, a quadratic like that and another quadratic that goes like this. Think about the slopes, see? So the slope over here is positive, right? Let's say it's, I don't know, 2. The slope over here is also positive, and let's say it's like 1. But the slope over here at the maximum is how much? It's a flat line. The slope here is equal to 0. And so wherever the slope equals 0 is a max or a minimum. You can do the same exercise if you have something that looks like that for a minimum, right? I don't know why I drew two maximums. So for a minimum, it's the same idea. So this slope here is, I don't know, -2. Then this one is, I don't know, -1. And this last one is a slope of 0. And so wherever the slope of you have a slope of 0, you're finding the max or min. Here they're asking for greatest speed. And so on greatest speed means you gotta do the derivative of something equal to 0. Because it says hence, you gotta use something from before. So okay, get the acceleration and equal it to 0, right? And so here you did the derivative of velocity and you equaled it to 0. So you're finding wherever the acceleration equals 0. And for part C, you can take your acceleration formula from here and equal it to 0. And so a equals 0 is going to give you -3t squared plus 7t minus 2 equals 0. And so from here, you need to find a way to solve for it. Now, technically, you have two approaches. On the one hand, from here, because it's the context of a squared, ax squared plus bx plus c, you have two main tools. One of them is what we call factoring, and the other one is what we call the quadratic formula. Now, I know that factoring is a little bit more fancy and is actually usually faster, but the quadratic formula is one that always works. And so I'd rather show you maybe the longer process, but the process that always works. So the quadratic formula, I think, is in here. There it is. So solutions of a quadratic equation is right here. See? And so as I was saying, whenever you have a context of a parabola equaling 0, which is exactly what's happening there, right? You can use this guy here. And so this guy here, what it gives you are the solutions for x, right? Where the whole thing equals 0, okay? Now, what is a, what is b, what is c? We'll take a closer look. A has an x squared next to it. B has an x to the power of 1 next to it. And C has nothing next to it. Or, if you recall, an x to the power of 0 next to it. See? So, remember how you want, but basically, A, B, and C is defined by what x it has next to it. See? So if it's x squared, it's going to be A. If it's x to the power of 1, it's going to be B. If it's x to the power of 0, it's going to be C. So from here, be very, very organized in your approach. And I suggest take a moment, write down what A is, what B is, what C is. So A in this context is -3, B in this context is 7, and C in this context is -2. What was my formula? My formula from here is going to be -b plus or minus square root of b squared minus 4ac divided by 2a. So you plug all of this in into that formula here. What you end up with is -7 plus or minus square root of 7 squared minus 4 times -3 times -2 divided by 2 to the power of a, which is -3. And so -7 plus or minus square root of 49 minus 4 times 3 gives me 12 times 2 gives me 24 divided by 2 times -3 gives me -6. So from here you end up with -7 plus or minus square root of 25, because 49 minus 24, divided by -6. So -7 plus or minus 5 divided by -6. So you from here, you're almost done. See? From here, the weird thing that's going on is that you have a plus or minus. So what the heck does plus or minus do? Exactly what I'm telling you. It's plus or minus. So you have one answer that is plus, or the other one, which is minus. And usually, depending by context, it's pretty obvious like which one you take. But I'll explain in a second how that applies here. And so up here, I can do -7 plus 5 divided by -6. And for the other one, you can do -7 minus 5 divided by divided by -6. And so this one up top ends up being -2 divided by -6. And this other one ends up being -12 divided by -6. So this one up top is going to be +1/3, And this one on the bottom is going to be positive 2. And so basically what it's saying here is that you reach, okay, a maximum. Here's the thing. Let me be a little bit more clear. So the greatest speed is reached at t equals 1 over 3 or t equals 2. Now here's the thing. You don't know if this is a maximum or a minimum. You just know that these are optimization points, okay? And so the greatest speed is either at t equals 1/3 or t equals 2, okay? That is sort of like the main idea, okay? That is sort of like the main idea. And so from here, what you gotta do is plug in t equals 1 over 3 into one of your formulas to see what like speed you get, right? And t equals 2 as well to see what speed you get. And so you can plug in into your velocity formula 1 over 3, and you can also plug in into your velocity formula the value of 2, see which one is bigger, and work from there. So if you plug in 1 over 3, you end up with negative 1 over 3 cubed plus 7 over 2, 1 over 3 squared, right? Minus 2 times 1 over 3 plus 6. And if you plug in 2, you end up with negative 2 cubed plus 7 over 2, 2 squared, minus 2 times 2 plus 6. And so this one up top, as you can see, ends up being negative 1 over 27 plus 7 divided by 9 minus 2 over 3. Now let me make a little bit of space here. So this point is k plus 6, right? While the one on the bottom ends up being negative 2, 4, 8. So negative 8 plus, this is times 4, so you end up with 28 divided by 2 minus 4 plus 6. And so from here, you kind of have to tell which one is bigger, right? Which one seems bigger, which one should be bigger, etc. And so right off the bat, you actually can say that the one on the bottom is a little bit bigger because 28 divided by 2, you can simplify it immediately. And this gives you positive 14. And so, damn, basically, from here, you end up with 14 plus 6 gives 20, minus the 8 and the 4 is minus 12. You end up with a velocity or speed of 8. While this one up top, do you think you get anywhere close to 8? Think about it. You have a 6 plus a 7 over 9, which is a little less than 1. So, I don't know, imagine it as like 0.8, okay? And you have minus 2/3, which is minus 0.66, and minus 1 over 27, which is like minus 0.01. Again, I'm just making some of these numbers up. This one is legit. But I'm making some of these numbers up just so that we understand the magnitude of the numbers. And you can immediately tell, yeah, velocity of 2 is going to be way bigger than velocity of 1/3. Okay? Another way that can sort of make sense is that you're substituting the larger possible t value into velocity, right? That one's a little more debatable, but I'd rather show the full process. You can compare both, and eventually you realize up top you have a bunch of fractions. On the bottom you have bigger whole numbers, okay? And so your answer here was 8. And so for part C, plugging in t equals 2, you end up with uh, da, 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 speed of 8 meters per second, right? Because those are the units that we're working with here. So again, I would like to do the observation that for part C, the amount of points was 5. So definitely more time taking, definitely harder. If you feel frustrated, it's pretty normal. part C is hard. Okay, I want to give you the tranquility that this stuff is not easy. All right, but the fact that you're watching this video and putting the effort goes to show it's gonna pay off. So keep it up. All right, whatever you're doing, keep it up. You got this. Don't give up. For part D, we need to find the greatest speed reached by the object for the time between 0 and 4. And so here it might be a little bit confusing. And so you really need to understand, like, what's the catch, right? And so on the one hand, I already told you that we found the greatest speed. And so we found the two optimals, which was at t equals 1/3 or at t equals 2. But the thing is, that was... here's the thing. I think this is the best way to explain it. So, um, even up here, it's pretty explainable. So I'll do it here. See? So if you look at your graph, right? If you look at your graph, what you ended up with, or what they told you, right? What you ended up with is discovering that you have 2 points of optimization, right? So you found 2 points of optimization. You found one that was at t equals 1/3, and you found another one, correct? You found another one that was at t equals 2, right? So if you look at 1/3, you can see that this is a point of optimization because it's a minimum. And at t equals 2, which is around here, well, it makes sense. You end up with a maximum, right? And so here's the 1/3. Here's the 2. It makes sense. There's a min, there's a max. That's why it showed up when I did the derivative, right? I was asking my function, yo, where's my slope equal to 0? And it's exactly at 1/3 and at 2. But the thing that we need to keep in mind with this idea is that although this can be a min and this can be a max, technically our highest possible sort of value or velocity can also be elsewhere. Now, what do I mean by this? Example, imagine you have a function that looks, I don't know, something like this. Okay? And it's restricted. So you see, when I put those circles there, it means it's restricted. That is as far as it goes. And so if I go ahead and ask you, okay, like, where's the minimum? Some of you would say this, but technically your minimum value is this guy here. And so it's very important, and this is the main idea, it's very important that you consider plugging in, how should I say it? Plugging in boundary values, okay? Because you might find the minimum by doing the derivative and all of that stuff, but for finding the actual lowest value, or, the other way around, the actual greatest value, you need to plug in the boundary values, see? And now this that I did here for 1/3 and 2 and all that stuff is just a very visual appeal for this. But technically all you really need to do is plug in the boundary values and see if there's something there that beats the maximum you reached earlier, because it might be a scenario like this one here, right? Yes, you have a minimum right there, but your actual minimum value is this, right? Yes, you have, maximum, right? I'm not explaining myself well, but I think it'll eventually make sense. So let me go over it one more time. See? This is like a key point, right? As a maximum, but its lowest actual value is this here. See? So if I were actually, now I'm gonna nail the explanation. See? The reason you need to plug in boundary values, and again, sorry for not explaining it well the first time, but the reason for plugging in boundary values is that you can have a function that looks like this. You can have something that goes boom, boom, boom. Okay? And so, yes, you have a max here and you have a min here, but technically, this would be what we call a local max, and this is a local min. It's like one of the minimums, one of the maximums, but the actual minimum is this guy here. So this would be your global minimum, okay? And this over here would be your global maximum. And so yes, what happened over here is that we found the greatest speed reached by the object before it comes to a rest. So it's like before k. So it's the maximums over here. But technically you need to plug in the boundary values because this value can also be very big. See? And now you might be thinking, isn't that a negative value? And I say, careful. We're talking about velocity. So if you have a very big negative velocity, it means, for example, you're driving your car. So here you're like going forward, right? Technically, sort of. You can think about it that way for now. And over here, you're going in reverse. But maybe you're going way faster in reverse than you ever went forward. All right, anyways, that was a lot of blah blah. I hope I cleared up some ideas. But for part D, the greatest speed reached by the object from 0 to t to 4, you gotta plug in the boundary values. And so plugging in 0 doesn't make sense, because if you plug in 0 here, well, I mean, it might make sense, but if you plug in 0 here, this goes away with this, goes away with this, you end up with just plus 6. And so one of our maximums that we already found was a speed of 8. So unless we find something greater than 8, it's not worth it. So now let's try plugging in 4. If you try plugging in 4, what you end up with is negative 4 to the power of 3 plus 7 over 2, 4 squared minus 2 times 4 plus 6. And so v to the power of 4, v of 4 is going to give you negative, that is 4 times 4 is 16, times 4 is 64, so negative 64, plus 4 times 4 is 16, so it's going to be 7 times 16 divided by 2, minus 8 plus 6. And so, oof, I end up with pretty big numbers. Let's see what happens here. So negative 64 plus, and for this next one, right, this is just a quick sort of tip for simplifying fractions, but because you have a 2 on the bottom, it'd be pretty convenient if you had a 2 on top. So you can rewrite the 16 as 8 times 2 divided by 2 minus 8 plus 6. Why is that useful? Because now you can do boom, boom. That goes away with that. So now I can start combining like terms. You end up with the minus 64 minus 8 and the plus 6 plus 7 times 8. And 7 times 8 is going to give me, 8 times 8 is 64. So minus 8 gives me 56 plus 56. And so from here you can combine all of this. You end up with 56 plus 6 should be giving me 62 minus 64 minus 8, which is a pretty big value. So give me a moment. That gives me minus. Wow, I cannot do math today. You're never alone in your math troubles. So this gives you 62 minus 72. All right, so you end up with minus 10. And so the greatest speed, this is the thing. So if your velocity is negative 10, that means you're going like backwards in your car, negative 10 miles per hour. So your speed is 10. Think about it that way. Speed is always like thinking in terms of absolute value. Okay? And so in terms of absolute value, your speed was 10. Yes, yes, it's negative, but it's because you were going backwards. And so from here, the greatest speed reached, because the velocity gave you negative 10, you can say, I was going backwards 10 meters per second. So the greatest speed reached at t equals 4 ended up being 10 meters per second. All right? So think about it that way. That is for part D. And now part E, which is kind of crazy. They ask us to write down an expression that represents the distance traveled by the object while its speed, and notice, while its speed is increasing. Do not evaluate the expression. So this is more of a context problem, to be honest. It's a little bit more of a context problem. You need to understand when is the object traveling with its speed increasing. And so, well, this is pretty hard, but I'll try to explain it the best I can. So let me make a little bit of space here. See? So this is the last part of the exercise. you already have a lot of context of how the object behaves, where the maximums were, where the minimums were, blah, 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 blah. And the point is that you need to identify where the speed is increasing. And so this also has to do with understanding velocity, okay? And so you have to understand velocity in different ways when you have positive velocity and when you have negative velocity, okay? When you have negative velocity, think about it as like you're going backwards. Okay, but if you're going backwards, your speed is still up, right? Think about a car going like, think about it this way. If you're in a car and you're going backwards, but you're going faster each time, it's like you're going backwards, but you have your pedal to the metal, then your speed is getting higher. And so having that in mind, well, where is my speed increasing and my distance as well? We'll only focus on speed increasing. And so here we said we had a minimum that was at 1/3 and a maximum at 2. And so immediately you can say, so there is a speed increasing here. See? So one of your intervals is going to be this one, right? But technically from part D, you did just discover something very interesting. So from part D, you discovered that at equals 4, you have a speed of 10. So that means that at some point, you were going 10 meters per second backwards. Okay? Interesting. And so was I ever stopped in between? Well, what was K again? Oh, K is when the object first comes to a rest. So at K, you are not moving, and then you start going backwards. Okay? So think about it this way. It's like the ball, right? Or even a car, right? So it's like you're a car, see? And you're driving, yada, 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 yada. And you really wanted to go to Wendy's because you love Wendy's. It's the best burger place in the world. Double Baconator is one of the finer burgers and inventions humankind has ever done. And so you want to go to Wendy's, right? And so you're driving, and oops, you realize you went too far, right? You passed the Wendy's, right? Sacrilege. You passed the Wendy's, and so you hit the brakes. So think about it this way: you're going. You pass the Wendy's, and so you hit the brakes. Boom, and eventually you're stopped. Eventually you're stopped, and then you start going backwards in reverse, and your speed gains up again. That is what's happening. See, that is what's happening, and so technically, you can also say that from here to here, from braking and going in reverse, your speed is also increasing. And so the two intervals that you're worried about or that concern you is what I have in red. So technically, speed increases, and this is not my final answer, but just intuitively. So speed increases from 1/3 to 2 and from K, which is the stopping point, to 4, right? So K and 4 and 1/3 and 2. Okay? So this is what I need to put in like fancy sort of math language, right? But the idea where you understood it. So you're driving and you have a certain amount of speed. You pass the Wendy's, so you hit the brakes, and while you hit the brakes, velocity is dropping. Eventually you stop and you start going in reverse, right? Really focus on when speed is increasing. That is the main idea, all right? So speed increases from 1/3 to 2 and from K to 4. That being said, writing down the expression that evaluates the distance traveled, uh, so here's another buzzword we're talking about. Look at that. Distance. So remember a million years ago I talked about the difference between distance and displacement? Well, identifying the word distance is again a massive hint for you to go to the formula booklet and looking for distance. And once you find distance, you're going to see, okay, so distance is going to be the absolute value of my terms from the starting point to the end point. Now you have two different intervals, right? You have from 1/3 to 2 and from k to 4. And so technically from here, you need to express it with like the following idea, okay? You need to think about it as, well, first of all, you identify the intervals where the speed increases, right? And now, because you need to express it as distance, right? And now because you need to express it as distance, what you can think about it is that it's going to be basically the integral, right, of the part that is positive, so everything that's up here, right? And so for the part that is positive, everything that's up here, which is just this section there, the part that's positive does not need an absolute value, so you can just say for this first section, okay, the part that I'm putting now in green, is going to be from 1/3 up until 2 of your velocity function in respect to dt, right? Plus the integral of the negative portion. And so the negative portion needs to be an absolute value because you only care about when speed is increasing. You don't care that you're going backwards, right? And so this will have the absolute value of your Vt in respect to dt. And its starting point, as we said, is going to be k, and it will finish at 4. How do you know it finishes at 4? Because your domain was restricted all along to be until 4. Okay? So, ladies and gentlemen, this was quite an intense problem, I'm not gonna lie. But if there's one good thing about it, as I said way in the beginning, is that it tends to show up. So might as well get familiar with velocity, might as well get familiar with these formulas, and if there's something I can say is that the approach is usually like pretty similar. Like you usually they usually give you one of these, and you gotta jump from one to the other. Okay, and so that is one thing you need to keep in mind. Just integrals and derivatives. If you're not sure or forget how they were, remember it's in your formula booklet. Okay, the derivative of an exponent, the integral of an exponent is all right here. I know these formulas look scary, but think about it in terms of examples. So maybe just learn one example like really well, and you can apply that logic everywhere, and it's gonna be much more friendly. Guys, at the end of the day, it's making the formula booklet friendly. Okay, a lot of people, as I say, like take it for granted. Come on, I have the formula booklet the day of the test, so like whatever. It's like an answer key, like I'm good. But what does it help you to have the formulas if you don't understand how they work? What's the most efficient way to use them? What's actually in it? So study with the formula booklet, you guys. Do it. You can do really well if you get familiar with it. I assure you. That, ladies and gentlemen, is how you solve for number 9. I hope it helped.